Okay, good morning, everybody. Welcome to day 2 of L4DC. We've got an awesome program lined up for you today. Thanks for making it out of bed and getting here for this early talk, which I think is going to be really exciting. Before we get to that, we just want to kick things off with another quick message from our sponsors. So Siemens is another one of our silver sponsors, and we're just going to play a quick video from them that's going to tell us a little bit about the exciting work going on over there at the intersection of learning dynamics and control.
Is the only purpose of a building to provide a pleasant and comfortable living or working space? And what about an industrial plant or the power grid? Is it sufficient that they merely serve their original purpose? We think differently. Because every building, every industrial plant, and the power grid can do much more than the obvious. But only if we enable them to. With smart infrastructure, combining the real and digital worlds across energy systems, buildings, and industries. Making commercial, industrial, and business environments better. Making them more efficient, more human-centric. And in doing so, making everyday life better for us and for future generations. We believe that today, purpose must be much more than meeting current needs, much more than sustaining the status quo. Because growing challenges such as climate change, population growth, and urbanization require new thinking and acting. We know that resilient, adaptive, and efficient infrastructure is at the heart of this, which helps our customers achieve their business goals and pave the way to a better future. And we will make this happen by driving the digital transformation and generating value from data in order to raise the sustainability of our buildings and cities, of our industries and grid infrastructure. In other words, smart infrastructure is sustainable infrastructure.
Reminder, we still have sponsor booths over at the poster session, including Siemens, so please make sure to go and talk to them and find out more about what's going on. And so with that, I'm going to turn things over to Sarah Dean, who's going to be chairing the next session.
All right, good morning, and I'm happy to introduce Vikas Sindwani, who is a research scientist at Google DeepMind in New York, where he leads a research group focused on solving a range of planning, perception, learning, and control problems that arise in robotics. His interests are broadly in core mathematical foundations of statistical machine learning and in end-to-end design aspects of building large-scale and robust AI systems. For this work, he's received numerous awards, including the Best Paper Award at UAI 2013, the IBM Pat Goldberg Memorial Award in 2014, and was a finalist for Outstanding Planning Paper Award at ICRA in 2022. He previously headed the machine learning group at IBM Research in New York and has a PhD in CS from University of Chicago and a bachelor's from IIT. And I'm very excited to hear what he has to say today. I think this is where large language models enter the L4DC discourse officially, which is quite exciting. With that, I'll turn it over to you.
Thank you. Well, thanks a lot for that very generous introduction. I am delighted to be here. It's an honor to be giving this talk today, and oh my God, what an amazing venue this is. I thought I would begin by sort of explaining what this playful title is all about through an example. So we're going to connect to a large language model which has one eye and one arm. It's located in Manhattan, in the Google building on the 9th floor there. This is a UR5 robot. Actually, let's just connect to it now, just to sort of warm up for the talk. It's a UR5 arm. It has a relatively simple action space. It can do pick and place. It has a suction gripper, fixed base. It has a RealSense RGBD camera. What it's seeing is quite a simple workspace, which has 3 bowls and 3 candies. And this interface will let me speak to it. So I'm going to speak to it and see what happens. And I would hope that the robot's having a good day. And in case things go wrong, this is a risk. We'll just put all the blame on the LLMs, OK? OK, so first, the red bowl is Sarah's bowl. And the blue bowl belongs to Nick. Sarah's favorite candy is M&M's, and Nick's is Skittles. So the middle panel is the robot's responding. The font is small, so I'll just repeat what the robot says. The robot says, OK. Can you hand them their candies? All right, so the robot actually is responding with code. Robot.pick-and-place, M&M chocolates, go to the red bowl, and the Skittles go to the blue bowl, right? So that was successfully accomplished. So this is an example of complex reasoning. There are 4 entities here: Sarah, Nick, red, the red ball, the blue ball, the M&Ms. Actually, I misspelled the blue bowl here. But the large language model generates robot code that is able to sort of digest this somewhat complex reasoning task and perform as expected. Let's look at some geometric reasoning. Place the M&Ms to the bottom right corner. Place Reese's to the top left corner. Did I do it correctly? Place the Skittles in the middle of the other candies. So it has to figure out what other means. It has to do some geometric reasoning and hopefully does the right thing. Now let's torture the robot a little bit. Imagine the green bowl is a beautiful valley of grass. Robot responds, OK. Move the thing Willy Wonka is known for into beautiful valley of grass. OK, there there it failed. OK. It was supposed to pick up the chocolates, but OK. Can you cut the candy in half? No, I can only move them around. By the way, this large language model is for this robot, but it comes with its own opinions. So you can say, what is your favorite candy? I like Skittles. Can I take them from? No, I like Skittles. OK. So that's a warm-up. Let me come back here. So for the last few years, actually when I was preparing for this talk, my thoughts went back to the very first days of the robotics program at Google. And we were tasked with this mission of, this very ambiguous, ill-posed mission of somehow enabling robots to solve lots of useful tasks in human-centric environments. And the perplexing question that came up was, how come we have robots on Mars? We have robots building cars. We have robots that can backflip. But when it comes to the most mundane chores in a human home, chopping vegetables, folding laundry, cooking, washing dishes, there are no robots around that can do this, right? And so how do we make progress towards really getting robots in a human home? And this was very ambiguous, and we decided we are going to solve a collection of robotics benchmark challenges and treat them as sort of pieces of a jigsaw puzzle. And if we develop core capabilities on these benchmarks, we'll make progress towards this end goal. And in the process, we built a collection of simulators for many environments. We looked at many different robot embodiments. We had teleoperators engaged on these platforms, logging infrastructure, distributed training infrastructure, deployment infrastructure, and so on. So let me tell you what these benchmarks were. There are a couple of mobility benchmarks. So we put a fleet of robots, dozens of robots in Google offices. The goal is simply to go from point A to point B amidst humans for inspection tasks while respecting social navigation constraints. This is on a wheeled robot. It's a mobile manipulator with a parallel jaw gripper. This kind of a platform I can immediately see would not actually be useful in my home, because as you go from the kitchen to the living room, there is a drop, right? So you need legged platforms. So we built an in-house quadruped, and we defined a benchmark called Barker, which is essentially an obstacle course in a 5 meter by 5 meter space. The robot has to jump off from a table, has to weave through these poles, has to climb up an A-frame, come down, and then jump onto a platform. And this is to sort of see how we can get legged, what would it take to build legged platforms. So this was on mobility. All the videos you'll see in the talk would be 4x sped up. So these systems, when you actually see them live, they move slowly. They don't match human performance. So we had a couple of narrow benchmarks around high-speed whole-body control. The first here is playing ping pong. There are 2 variations of this task. First is to cooperatively play against a human as long as possible. Another is the targeting benchmark. I give you a strategic spot on the other side of the table. Can you return the ball so it lands close to that spot? And another benchmark was the catching benchmark. So we'll throw balls at this ABB arm. It has a mobile base. You have less than a second to plan the entire motion of the robot, and so do high-speed catching. Then we looked at manipulation problems. So the first one here is the same robot as the mobility robot, the wheeled system. We'll place them in Google cafes and task them with table wiping. On the right is Chad Badu, our lab manager in the New York lab, attempting to kinesthetically teach the robot to fold a T-shirt. So this is on manipulation. And then finally, language to actions. So we have a couple of different embodiments for this benchmark. The user gives a very long horizon task. I spill my Coke on the table. Can you throw it away? Can you bring me a sponge? So a very long, sort of complex, long horizon instruction that has to be mapped into the correct actions. These benchmarks were posed a couple years ago, and to be honest, we can do a poll here as to who thinks what's the most complex benchmark. But I was very skeptical about being able to solve these open-ended micro-kitchen tasks, going all the way from a long horizon instruction to actions that accomplish the task. But I think that the emergence of these reasoning capabilities in large language models and multimodal foundation models sort of provides a glimmer of hope that this can be done. So the agenda for today is I'll argue that there is an emerging control stack for human-centric robotics. It looks like this. We'll be talking about policies as usual, mapping observations to actions. These will be run through real-world dynamics, right? You get the next observation, the policy takes the next action, and so on. This is a classic RL picture. And the policy should perform well in closed loop and accumulate lots of reward. And in the process, we'll be collecting robot data to improve the policy. This is the low level of the stack, and somehow it'll talk to a large model that is set up to digest tokens and return tokens, and it's trained on very large data sets from the internet. And because these large models can understand language, you have an additional mode in which the whole system can interact with humans. This kind of a stack is analogous to the System 1, System 2 kind of a metaphor from Daniel Kahneman's Thinking Fast and Slow book, right? Where you have system 1 is the autonomous system, which is fast, instinctive, reactive, and it coordinates with system 2, which is a slow, conscious reasoner. And if something goes wrong, if system 1 cannot answer, then the reasoning goes to system 2 and so on. So it seems like this is an emerging control stack that is here to stay. So where I want to begin, though, is first share with you a few surprises while learning controllers on benchmarks, which I did not anticipate. And then a few recipes to connect foundation models and control. There'll be a few questions in the backdrop, not all of which we'll answer. So what are the interfaces? What do the large models know already, or can be trained purely in context versus learning from physical interactions, right? These trade-offs now emerge in the context of this modern control stack. And then there are a whole host of issues in terms of latency. The large models live on the cloud. The policies live on the robot. How will they talk? What's the latency? What's the cost of calling these models? The biases they come with, safety and robustness. OK, so this is a slide I put together actually a while back. This is my attempt to situate some of the findings. So this landscape, all the policies that we'll talk about are either originating from imitation learning approach, where the data is collected by a human, so teleoperators, or the robot is tasked with the data, and that's the reinforcement learning axis, right? And a few years ago, there was a lot of emphasis around reinforcement learning. We had the first project in the team was actually Q-learning-based, policy gradient methods, model-based methods, and so on, right? So many of these techniques have been developed over the years, and there have been amazing success stories around them. But this was not the starting point for us, in a sense. We were interested in the extreme points of these axes. So I'll talk about black box. So black box is an approach that, in a sense, treats the RL problem as a complete black box. It's not aware of the MDP structure of the problem. And how far can we push those methods, because they are simple and effective, and I'll talk about that. So the other point of interest in this plot is the origin, which is physics, this is where classical control lives, and you have optimal control here. So here, in this axis is supposed to be, on the left side, you have more and more dynamics awareness. On the right side, you need more and more data to compensate for lack of knowledge of dynamics. So this is where optimal control is, PD control, which is justified through stability arguments and so on. And it turned out that over the years, imitation learning sort of came back, and I'll talk about implicit policies, which seem to be quite promising. So this is a simplified picture in the sense that, obviously, a full control stack is a hierarchy. You could have a RL-based policy talking to a low-level motion planner, talking to a low-level PD controller, and so on. But when you combine these with foundation models, there's a very large design space. And what the foundation models bring to the table change the optimal point in this design space, right? So the three surprises for me was, first, the unreasonable effectiveness of zeroth order or black box optimization. Second, the reasonable effectiveness of optimal control. And third, the return of behavioral cloning or imitation learning and the promise of implicit policies. So let me quickly go through zeroth order optimization. So you have a black box. Inside the black box is a simulator or the real world. Policy parameters go in. The total reward comes out. We want to pose this as a reward optimization, policy optimization problem purely as black box learning. Right? So the algorithm here is really simple. You would like to take gradient-like steps. You don't have the gradient. So you replace this function by a proxy. So this is a Gaussian smoothing of this function that does not admit gradients, right? And then you estimate this gradient. So this is a sum of linear combinations of perturbation directions where the weights are given by these finite differences, right? So it's extremely simple and scalable. That's the algorithm. But if you look at sort of textbook wisdom, so this is Kahn et al.'s derivative-free optimization book, basically says don't attempt this for more than a few hundred variables. But it turns out to be extremely effective for learning in sim, followed by a handful of real-world iterations. It's doing a form of parameter space exploration with deterministic policies as opposed to action space exploration with stochastic policies. And it turns out this can be a more aggressive way to explore the policy space. Certainly don't do naive finite differences. You can get away with the number of perturbations being far less than n, and sometimes even one perturbation suffices. You can make the parameters structured, the perturbations structured. You can make them tolerant to noise by connecting this kind of gradient sensing to robust regression. And it surprisingly even turns out to be feasible for large language model fine-tuning in a very recent paper from Princeton. The idea is that the gradient here, being a linear combination of random perturbation directions, can be digested with minimal memory. You don't have to instantiate the PIs. You can create them, the perturbations on the fly, because these are random vectors. So for us, it initially was supposed to be a good starting point, but it turned out to be the best ending point too. This is something Dipali covered yesterday, the catching benchmark. The policy maps the ball state and the predicted trajectory to joint velocities. You have only a second to plan the whole body motion of the arm. There are some challenges here. It's not enough to treat this as an IK problem because you have to do cradling. So you have, there's a cradling maneuver to make sure the ball doesn't bounce out, which is captured in stability and orientation rewards in black box training. As the ball approaches the end effector, which is this lacrosse head, there's vision blinding. You cannot rely on the ball state anymore. That's why you need a predictor in the whole system. And surprisingly, this is a complex problem because of drag and Magnus effects that can deviate from projectile motion. Surprisingly, it turned out, even though the policy had thousands of parameters, a handful of fine-tuning iterations in real sufficed, resulting in 85% catch success. Is this good or bad? I don't know. It's better than the Indian cricket team for sure. 7 millisecond reaction time. And this benchmark became a test bed for high-speed perception to action, where we were comparing pure learning versus pure control approaches. It's presented at L4DC yesterday. So it turned out that these methods were at the core of graduating this benchmark. The same was the case for the ping pong benchmark. It was compared against many different RL approaches. It turns out that it won the internal targeting challenge with 26 centimeter error in comparison to other RL approaches. It turned out to be at the core of an iterative sim to real fine-tuning approach that demonstrates very long rallies against humans. And this is appearing in the RSS paper here. Turns out to be the most successful and reliable method applied in the system. So this was a surprising finding. The next one is reasonable effectiveness of optimal control. So this is the standard optimal control problem, right? Constrained optimal control. It's dynamics aware structure. As you know, it's very challenging and very non-convex. In our group, the effort was to develop new second-order solvers that are robust while trying to get real-time performance via JAX, and Stephen and Sumit covered this in a tutorial a couple of days ago. We developed new solvers. Also, since these solvers are implemented in a framework like JAX, an auto framework like JAX, the solver solution is also differentiable, meaning you can connect these with deep learning backends and do end-to-end learning. So I'll talk about learnable MPC in a little bit. An open source library, the link to the JAX tutorial. By the way, we are interested in using this both as a controller in an MPC setting, but also as a feasibility reasoner in the sense that if you attempt a task that is not feasible, the feasibility is captured in this from the optimizer itself. So we can return back to the large language model that this task is not feasible, the red block cannot be reached, so please move it closer. This kind of feedback can go back to the human. It turned out that until 2021, the team was very RL focused, but going back to optimal control in MPC actually dramatically improved performance. It turns out that better solvers lead to improvements in solving the hardest scenes. It's when you see these wheeled robot fleet, the entire fleet now uses MPC. And then for fine-grained attention to high clutter scenes and for social cues, we used a learnable MPC approach. For catching, many interesting trade-offs emerged. So first, the fact that these solvers in JAX can give you real-time performance. That was great to see. There's robustness to distribution shifts. So if you compare black box against MPC approach, it turns out if you deviate from the training distribution, the MPC is, so if you start throwing the balls much slower or at angles that the robot had not seen during training, the MPC approach is actually much more robust to that. And furthermore, it shows a more versatile multimodal behavior in terms of left and right catching on both sides, as opposed to the black box policy. So this was, so in other words, MPC, like it's not the case that every single time learning would win, which is the philosophy with which the team sort of entered these benchmarks. The return of vanilla behavioral cloning. So why did this happen? So first, quasi-static tasks like pick and place, they're easy to teleoperate and collect data at scale. When the visuals and semantics is complex, it's hard to simulate these things and jumpstart RL. The projects that attempted to do this end-to-end, so pixels to torques, ended up having extremely long development cycles, many years to go from the start of the project to the actual final publication. Also, because of foundation models, the focus shifted on short horizon policies running for a handful of seconds. And in these short durations, behavioral cloning tends to be stable. You don't need Dagger-like ideas to stabilize these policies. Again, this is the first connection back to language here. So short sentence conditioning works. What I mean is, and then so this is a approach to build policies that will operate over a short horizon. They will be sentence or phrase conditioned, and then they'll be orchestrated at a high level by a large language model. Two projects from our team. One is RT1. This is solving 700 tasks in a micro kitchen on a mobile manipulator. It's a policy, a transformer-based policy that takes instructions and images, maps it to actions that in this case were discretized, which there's a mode that dictates whether to move the arm or the base. Again, like, right, so these are the results, and on the right here, you can see pretty high success rate on tasks that was seen during training, but the positions of objects were randomized and so on. So these are tasks like pick up the chips from the table and Coke cans and place them somewhere, open drawers and things like that. A fairly broad range of tasks you could do in a micro kitchen. And so these are the generalization results. It seems to be, it's fairly robust to variations in the background and distractor objects and so on. So this was one project. Another project was interactive language. Here, these are tabletop pushing tasks involving simple shapes. Again, vanilla policy, similar, a different architecture, but the same idea, which is to essentially use transformers to map a sequence of images and the instruction into a common embedding space, and then use the self-attention mechanism, and then finally map it to the action space of the robot, in which in this case it's the position XY and the direction of the push. 600,000 teleop demonstrations were collected, and again, like this is 93% success on 87,000 instructions. So this is another example of just pure behavioral cloning sort of working out of the box. Okay, I want to talk about implicit policies. Explicit policies map states to actions using standard feed-forward modules, neural network libraries, and so on. By implicit policies, what I mean is the mapping from state to actions involves an optimization problem. So you're minimizing some kind of an energy function or an objective function, which is parametric, right? And there's a sampling version of this, which is energy-based models. So you can define a distribution that's proportional to the exponential of these energies. And so you have a state-dependent energy landscape in the action space. And by solving this optimization problem or sampling in the space, you get actions. So essentially, you're composing argmin on top of there's an argmin operator composed with a traditional deep learning backend that parameterizes an energy, state-dependent energy landscape. So this is one flavor of implicit policies. Another flavor of implicit policies is where you have a state-dependent vector field in the action space, and starting from different initial conditions in the action space, you arrive at your final actions. Right? So why implicit policies? Well, there's argument that it can model discontinuous state action dependencies better. If you're using EBMs, it can capture multimodality. And then we'll see a bit later how we can incorporate MPC-like priors, dynamics awareness into these models. One point here is parametric optimizers and ODE solvers, which are bread and butter, I would imagine, for L4DC. They can be embedded into deep learning pipelines via custom vector Jacobian product operators in these authoritative pipelines using sensitivity of solutions. For instance, for optimization, the kind of sensitivity you can get by using the implicit function theorem. Why implicit policies again? So here's why can they model discontinuity? So here's, suppose you're trying to fit the step function. You have a degree 4 polynomial and a degree 20 polynomial, right? And you can see the Gibbs phenomena here. It struggles to actually fit a discontinuous function. But let's say we define fx as argmin over y of pxy, where pxy is a degree 4 polynomial, right? So on the x-axis, on the axis there is y, and on the y-axis is p of xy. You can see that anytime x is positive, these are the red curves. They bottom out at +1, and anytime x is negative, which are the green curves, they bottom out. They are minimized at -1. So then fx is really a composition of argmin operator with a degree 4 polynomial is actually able to model the step function, right? So when you combine implicit policies with behavioral cloning, you get this extremely fine type of nudging, contact-rich type of behaviors that that explicit policies are not able to match. So this is the implicit BC work from our team, and on the right side is a diffusion policies work in a similar vein from Columbia. Okay, in the interest of time, I'll skip this slide, or I'll go through it very quickly. So multimodal transforms, a few key ideas. You have text and images. All modalities are treated the same way. You have a tokenization process that ultimately lands you in some common embedding space. So you have x naught of theta e are embedding parameters. You have transformer layers that then take these token embeddings and process them until you land at a final representation. And from this representation, you construct a downstream object of interest, like a probability matrix that is a matrix whose rows, this is NV by N. N is the number of tokens. NV is the size of the vocabulary. Sigma S is a column-wise softmax operator. In other words, you get a probability distribution over your vocabularies, and then you can, the last column of this matrix is what you can use to continue the sequence, right, by sampling from it. So training involves optimizing log prob over, so you take fragments of these sequences from the internet, and you apply the log prob loss, and at the bottom is shown how you can start with, given a prompt X, how do you construct these probabilities from the transform architecture and sample from it in order to autocomplete the prompt, right? The core of these is the attention block, which is essentially a sort of a cascade of convex representations where you're looking at quadratic interactions between your token embeddings. You might have a masking matrix to prevent things that you don't want to interact from touching each other. But really, you're taking convex combinations of your big capital X matrix and then doing a linear affine transformation h times, where h is the number of heads. It turns out that this kind of a block, the capacity of this kind of a construction is, we're just starting to understand what it can do, why it can do what it does. So for instance, it can emulate linear algebra operations. So the map from x0 to xt, suppose that map is something like a eigen decomposition, then it turns out that you can set the parameters of these transformer blocks in a way that you can make it do linear algebra. Or if you pack into the prompt a collection of in-context training examples, little xy pairs, then it is as though, when you do the inference, it's as though you're doing a form of training and estimating a model in order to produce a prediction on the task, which is also packed in the prompt. All these steps give you a base model, which are then fine-tuned for a task of interest. You can have, until now, this was all about single token prediction, but you can roll out multiple tokens and then evaluate the quality of those tokens with a learned reward. That's the RLHF framework, and you can do multi-step tuning, which gives additional gains. At the end, you have a foundation model that has prompt, task as input, prompt plus task, and theta are the big parameters, right? And given this, it'll generate tokens. And there are a couple of distribution shifts to watch out for. One is the internet to prompt distribution shift, and the other is prompt to task distribution shift. And anytime these are messed up, the model might behave in an unanticipated way. In general, the generalization radius of in-context learning is poorly understood. I have a few more minutes. So first, I want to talk about a few recipes to connect the transformer world with classical controllers, and a few recipes to connect foundation models with controls. So let's talk about transformers and MPC. So these are situations where MPC struggles, very high clutter and picking up very subtle social norms. These tasks need very fine-grained attention to highly localized clutter and social cues. So one way in which you can combine transformers with MPC is an inverse optimal control approach. So what we do here is to take the MPC cost, the base MPC cost, but then modulate it with a quadratic term, which is coming out, which is actually a reshaping of the output of the transformer after it processes a observation, right? Furthermore, when we talk about foundation models, MPC, the latency is always a concern. So we want to retain the real-time benefits of MPC. So here we use a variation of transformer called performer for fast attention. What it does is to essentially work with a low-rank decomposition of the attention matrix, which is an n by n matrix, where n is the number of tokens. Without such a decomposition, it would be infeasible to process images at a very fine pixel level. This whole thing is trained using bi-level optimization, where the upper level is imitation loss, is optimizing for imitation loss, the transformer parameters, while the lower level is generating MPC trajectories, transformer parameterized MPC trajectories. This kind of a cost structure, it enables fast attention. It enables cheap quadratization if you're using iterative LQR or other such techniques for trajectory optimization, and it leads to stable training. Again, it uses the fact that the MPC solver itself is differentiable. So these are some results. Learning an MPC solver like this gives more robustness. It gets stuck in local minima less often. It can navigate through scenes of extreme clutter more gracefully. And this example shows how it's again trained on teleop demonstrations that's more graceful in social settings. Let's talk about long horizon orchestration of short horizon policies. Right? So the kind of thing we want to do is, so here, bring me the chips from the drawer. The robot has to navigate to the drawers. It has to open the drawer, take out the chips. Some unanticipated things might happen. In this case, a Googler is injecting adversarial disturbance. Take the chips out of the drawer, bring it to the user, put it down, right? So I'll talk about a couple of different recipes. One is the SECAN recipe that is illustrated here. So on the left is a large language model. It's prompted in a certain way. In the SECAN paper, it's prompted using 17 examples of the following template. The human colon, how would you bring me the peanuts? Robot colon, step 1, step 2, step 3, step 4, right? And then, so this is how it's prompted. And then at test time, you give it a task. How would you put an apple on the table? Now, the LLM itself is blind. Whether it should find an apple or whether it should pick up an apple, it has no idea how to figure that out, right? This is encoded. The policy is what's not blind. The policy, in this case, is the RT1 policy that I talked about earlier. So those are the policies shown on the right. So the policies are paired with a value function. The large language model is not allowed to hallucinate. It's constrained to only score sentences that are associated with the sentences that RT1 understands, right? Again, the policy and value functions are learned separately, and the value function itself can be fairly crude. So the LLM probabilities, the likelihoods, are multiplied with the value functions to actually reorder the set of skills that should be invoked next. So this was tested in 101 micro kitchen task. It resulted in 84% planning success and 74% execution success. If you don't use value functions, the planning accuracy drops. If you send the entire long instruction into the policy, into RT1, and don't have the LLM, the performance drops to 0 because RT1 was not trained for long horizon tasks. If you use a weaker LLM for language tasks, it turns out performance drops. And if the policy fails, there's no feedback back to the LLM. So this is one recipe. Another recipe is a PAMI recipe, which is, this is just to show a couple of different trade-offs in this design space. PAMI is I think it's a remarkable model. So here are some examples of what PAMI can do. It's a generalist. It's not just meant only for control. It's a multimodal reasoning model. So this is an example of the kind of reasoning it can do. So you can give it 2 photos. So it can take both text as input as well as images. So photo 1, photo 2, what's in photo 1 but not in photo 2. And then you add to the prompt. This is the chain of thought prompting. Let's think step by step. And the model responds, well, photo 1 has sunglasses on top of the folded clothes. Photo 2 does not. Therefore, sunglasses are in photo 1, but not in photo 2. This is the kind of reasoning that just emerges from these models. You can also deploy it on a robot, show it a scene, and ask it what it sees. And if the human asks me to do a certain task, what are the steps to invoke? It's using exactly the multimodal transformer construction I talked about. So again, it uses a PALM model. It's a large 562B parameter model. It uses a pre-trained, which is a combination of the PALM large language model. So 540B parameters are coming from there, and 22B are coming from VIT, a vision transformer. So these are already pre-trained with reasonable weights, and now they are fine-tuned on robot data, where the data is of this form. So human gives an instruction, the robot has the step history, IC image, so you actually literally insert the image there, and the robot then has to predict the next step of the plan. So it's fine-tuned on data of this kind. What's remarkable is the fine-tuning is only done on about 2,000 such sequences. This model does not need to rely on in-context learning as much. It's effective despite limited robot data. After each step is decoded, it's again passed to RT1, exactly as in the SECAN recipe, until the policy terminates. And this has the video that I showed earlier of bring me the chips. You could see it could resist. That was a PAMI model. It could resist adversarial disturbances. But the trade-off here is because this model is not blind, you also have to ship the images to the model, so that adds latency. Another trade-off is the risk of catastrophic forgetting. If you don't use large enough models, when you fine-tune on limited robot data, the model actually starts to forget its linguistic capabilities. So these are some trade-offs that emerge when you do fine-tuning. Code as policies I already talked about. So in the interest of time, I will end my talk here because it's 2 minutes late. Thank you.
All right, thank you so much. I think we have time for a question. If the next speaker the first speaker in the next section could also come up and begin setting up. In the meantime, take a question. No, maybe too much pressure that it's just the one. All right, I guess I'll ask one question in the meantime. So do you think that, do you see the language models as living a level above all the control stuff that you began with, where it's helping with planning, or do you see language models as playing a role at all levels?
I think one of the points I was trying to make is that this design space is fairly large, and I tried to show a few different recipes. The transformer MPC recipe was very tightly integrated. That's like a controller with a transformer-like backend as very tightly connected to it, and that connection was being done through custom VJP and so on, right? Like auto diff completely through. Take a classical controller and provide it a transformer backend. Most of the recent work that's happening is of the flavor of a low-level stack talking to a large language model in a somewhat decoupled way. And again, there are trade-offs there where the large language model is doing only pure planning, which was the case for SECAN, or it's actually also doing some kind of feedback control, which was the case in PAMI, because PAMI is a model that can also it shares an observation space with the robot. So I think the design space is very large, and can we unleash all L4DC tools to sort of understand the best points in this design space?
Interesting. Awesome. Thank you.
Thank you.
Let's thank the speaker. But at the coffee breaks, yeah.
Everyone, welcome to the first oral session for today. We have 4 exciting talks in this session. The first one is from Sumon Koga on policy learning for active target tracking for continuous trajectories.
Thank you, Yannis, for your kind introduction. And good morning, everyone. My name is Shumon. I'm a postdoc at the UC San Diego. Here I present a work on policy learning for active target tracking. We are focused on the active target tracking problem, which is to plan the trajectory of a sensing robot to reduce the uncertainty in the state of the dynamic target of interest, which has been motivated by diverse applications such as wildfire detection, security and surveillance, and pursuit evasion, and so on. While the traditional active target tracking problem has been studied by the method of optimization and path planning based techniques, this work considers how to run the control policy for active target tracking that generalizes to the different target configuration and motion. The earlier work has proposed a deep Q network for the active target tracking problem, which is a model-free learning method over discrete action space. Our prior work has proposed instead proximal policy optimization over continuous action space, which is still a model-free learning method. This work is the first one which proposes a model-based learning method for dynamic target tracking problem over continuous action space. Let me present how to formulate the active target tracking problem. We consider one single agent and multiple targets, where the single agent follows the S33 motion model for a robot pose state, which includes both the position and orientation states for a given velocity input. And each target motion model is supposed to follow a linear Gaussian model. The onboard sensor attached to the mobile robot returns the sensing states for target states only within a limited field of view for the agent, the vision. Using the obtained sensor states, we employ a target estimator by a Kalman filter online, which has the both prediction step and update steps. However, the update step for the update step is done only for targets within the field of view. The problem we tackle is to run a control policy to maximize the log determinant of the information matrix at terminal time. Since the sensor equation with a limited field of view is not differentiable with respect to the robot pose state, we introduce the differentiable field of view in the information update steps in the Kalman filter, where we introduce the signed distance function, which returns a negative distance from a coordinate q to the set f, which is the field of view, if the coordinate q is within the field of view, and it returns the positive distance otherwise. Also, we introduce a function phi, which is a probit function approximating a discontinuous step function by a continuous smooth function. Here, in particular, we chose the Gaussian CDF function. This figure shows the visualization of the differentiable field of view, where we observe a smooth transition from the unobserved region to an observed region ranging from the value 0 to 1. Then we develop a model-based reinforcement learning algorithm to obtain an optimal policy parameter given an initial guess of the policy parameter. What's happening inside the model-based RL is the computation of the forward path for the robot pose state and predicted mean and information in the Kalman filter with a differentiable field of view. And also, we introduce the sensitivity variables about these states with respect to the policy parameter, which is also computed in the forward path. And after finishing the computation in the forward path, we calculate the gradient of the reward value with respect to the policy parameter using the terminal condition of the sensitivity variable. Then we update the policy parameter by a gradient descent and keep repeating this computation iteratively. More in detail, we show a proposition stating that the analytical gradient of the reward function with respect to the policy parameter is given by a trace operator with respect to the sensitivity variable, which is obtained by taking the derivative of the log determinant, where the update of the sensitivity variables are obtained by taking the gradient of both the information update in the Kalman filter with differentiable field of view, and also taking the gradient of the robot S33 motion model. To enable the training of a varying number of targets, we introduced the attention mechanism in the network architecture by separating the layers for robot pose state and predicted mean and information in the Kalman filter. And also, we introduced the padding and masking to eliminate the redundant layers at the end. We trained the two control policies. One is based on the proposed model-based RL method, and the other is based on the model-free RL technique. And the training has been done over randomized initial condition and randomized number of targets. Here in particular, we tested over 3 to 8 number of targets, as well as the randomized bias in the target motion. After sufficient amount of training, we have tested the obtained control policies for 3 scenarios, the 3, 5, and 7 number of targets. And there, we observed that proposed model-based RL efficiently observes the moving target compared to the performance under model-free RL. As a quantitative analysis, we also observed that the model-based RL achieves a superior performance in terms of the larger mean and smaller standard deviation in the episodic reward after sufficient amount of the episodes. To conclude, we have proposed a novel model-based reinforcement learning algorithm for an active target tracking problem over continuous action space associated with the SE3 robot motion model, where we employ a differentiable field of view in the reward function and derive the analytical gradient based on that, and design the network architecture with attention mechanism to enable training over a randomized number of targets, and demonstrated the superior performance in uncertainty reduction in the target states compared to a model-free RL methods. As a future directions, we are interested in several extensions of the RL for the active target tracking problem, where we are interested in considering environment with obstacles, where we model the occlusion of the field of view, as well as the collision avoidance, and also the unknown number of targets, where we potentially require dimension varying Kalman filter, and also the unknown and general target dynamics, where we are interested in applying the conformal prediction to guarantee the probabilistic bound in the unknown target states, and also the multi-agent RL algorithm by employing the graph neural network the design. Thank you very much for your kind attention, and I'm very happy to take any questions.
Time for one quick question. In the meantime, I will invite the next speaker to come on stage.
Hi, thanks for your talk. So I have a question for regarding the order of the tracking targets. So in this case, you have multiple targets to track. So how do you determine which one to track first and which one to track next?
Thank you very much for your question. That's very good, good point. And the algorithm tells the priority based on the uncertainty for each target, which is computed by the information matrix for each target. So essentially the agent tries to view firstly the target which has a higher uncertainty.
In that sense, it's kind of greedy, right? Because you only rank the most uncertain or the least uncertain one, but not like the entire for all the targets, right?
Yes. So because we are considering the field of view, it's possible to observe multiple targets at once in a shorter time. So essentially every strategy is based on maximizing the information, the variable about the entire target states.
Okay, thank you.
Thank you for your question.
So we can proceed to the next talk, which is from Bilhan Sel, who will talk about learning to learn to guide random search derivative-free meta black box optimization manifolds.
Thank you to everyone for being here. I'm Bilhan Sel, and I'll present the work on learning to learn to guide random search derivative-free meta black box optimization on manifold by the authors you see on the screen from Virginia Tech and Berkeley. Without further ado, we can get started on what we mean by derivative-free and meta black box optimization. Here we assume an online sequence of tasks that arrive one by one, and for each task we wish to solve a high-dimensional stochastic optimization problem of this form, where we are only able to get noisy but unbiased estimates of the value of the function. This means that we cannot simply query any samples for the gradients of the function at any point. So if we wish to obtain a gradient information, we will have to use some form of like sampling and then trying to get the gradient from that point on. And the main difficulty in the setting is that the optimization complexity heavily depends on the number of the dimensions represented by D in this slide and the following slides. And one way of reducing this curse of dimensionality is by leveraging the idea of considering that the high-dimensional functions mostly rely on latent low-dimensional manifolds from this work, Senner and Colton. And one thing to note here is that we do not assume this manifold to be like stationary, meaning that the effective dimension or the structure of this manifold can change throughout our optimization trajectory. By uniformly sampling from a lower dimensional uniform sphere and lifting it to the input space of the function that we would like to optimize, we do get a simple way of representing this by phi r and phi h parameters, and by orthogonalizing the partial derivatives of this function or r with respect to x, we can get an estimate for the unbiased gradient of the smooth objective. So in order to show our theoretical guarantees, let us get started for the online stationary regret for a single task. Here we conveniently alter the right-hand side to take the optimization trajectory and its distance from the starting point to take into account, which will be useful in the coming results. And similarly, we also show that we also want to show something similar when we optimize the latent lower dimensional manifolds. So in order to show our final convergence, first we need to define what is the function that we would like to minimize. Here we define the task average regret on stationarity, where m is the number of the tasks. And if you remember, we consider the online setting, where the tasks arrive sequentially, and the xi represent the points we arrive after the capital T number of optimization steps with some written task solution algorithm. In our case, we use the learned manifold to random search algorithm again. So for instance, in the remaining slides, we will focus on what we can learn about the initial search point and how well we can optimize for the starting manifold. If you consider this definition for the UIs, and where the xi1 is the initial search point recommended by our meta algorithm, we can see that this can be averaged on the different online tasks we see to be an upper bound on the task average regret on stationarity. By altering a popular optimization algorithm named follow the regularized leader to be the follow the regularized meta leader, by changing the last functions as we see on the second term on the right-hand side at the bottom by the UIs, we can later show that we can optimize for UIs in the simple way, since we previously made the decision to make those functions dependent on the optimization trajectories. It is common to define a task similarity measure in meta-learning algorithms, since conceptually some tasks distributions will be more difficult or easier to learn than the others. In our case, it is natural to represent this similarity between tasks based on the initial starting points recommended by us by our algorithm. I want to remark that we did not complete the algorithm yet, so we defined the measure for any starting point for all the task distributions, this V star. And the initialization represented by our regret for the best initialization point, depending on within any task algorithm. Again, in our case, we use the learned manifold random search. By this measure, we can show that, first of all, our main results, that by running a slightly modified follow the regularized meta leader, we can decay to this best initialization points. Now for the second set of results, we focus our attention to the meta-learning of the search manifold By following a similar pattern, this time we define these UI primes, where the input phi I0 are the meta-initialized starting manifolds. And since this can be a highly non-convex function of the manifold parameters, we need to use something else than follow the regularized meta leader as we did previously. Here we follow follow the perturbed meta leader. Here the assumption of being able to find the gamma tau approximate solution points might look limiting, since they could be perhaps quite large, like with the Witten-Task optimization. In practice, however, we see that due to the learning capabilities of neural networks, we can highly accurately represent those true lower dimensional manifold input space of the functions that we would like to optimize. Continuing by using this follow the perturbed meta leader algorithm, we give our second result where we see that we can also bound the task average regret, again this time, in terms of initializing the manifolds. Previously, we were doing it for the initial search point independently. And again, to reiterate, the gamma and tau that appear in this bound are relatively small in practice. And since we have two separate bounds on the task average regret on stationarity, we can choose this, we can choose to add this kappa between 0 and 1, so that we can also accelerate or try to get this trade-off between learning a better initialization point or learning a better manifold parameters. That we can in the end choose whichever one is smaller, so that the end algorithm will perform at its best. So that way we can get this following results. And so for our experiments, we evaluate our approach on Mujoka environments, which are relatively high-dimensional continuous control tasks. We use multi-layer perceptrons as our parametric functions, both for the learning of the manifold and the actor agent in these RL tasks. So the parameters of the neurons of the actor are basically the starting points that we wish to find for the initial search points, and also for the manifolds, again, we are using multi-layer perceptrons. For all the environments, we chose a latent manifold dimension of 50. However, the true number of parameters, like the neural network parameters, the axes are actually higher than 100,000. And in these plots, we see that the meta LMRS which is our algorithm, our proposed algorithm, is able to quickly adapt to new tasks. Here, the pre-trained model is trained on one of the tasks in the task distribution and tries to adapt to new tasks. Although it might seem that it's not learning anything, it's actually learning very slowly, the pre-trained model, the one that's shown in red. And the same is true for the random initialization. And also, some question do we really need to learn both the initial search point and the manifold? We have this ablation study. Here we see that at the bottom with the blue one, where we only do manifold learning, it doesn't seem to be helping much, which makes sense. However, when we just learn the initial search point without learning the manifold itself, we see that the end performance is not as good as learning both of them at the same time. And I believe this is the end of the presentation. So thank you for your attention. Thank you.
Great. I think we have time for 2 quick questions.
Hi. Thanks for the talk. It's kind of incredible that such a large network can be only embedded into a 50-dimensional latent dimension. Could you comment a bit more about the intuition for that?
Yeah. Thank you for that comment. So the question is, we are talking about 100,000 parameter in a neural network, but in the end, we seem to be just using 50 dimensions. One of the reasons is this, this is not just starting, after we train our meta training algorithm, it tries to learn a good initialization point, and after that, we say that, okay, there aren't actually that many important, perhaps, number of search directions. So this is one of the results. We don't just learn with the 50 dimensions at the first. And also the other thing is this, as it learns a new like a new, trying to adapt to a new environment, those 50 dimensions are also, they are not stationary, right? So they can also adapt. Basically, after we do this, they can also change quickly to take into consideration of the important function as well. So yeah, even though it seems 50, like the effective dimension of it, I believe is kind of higher than that. I mean, this is at least we see in the empirical results. So thank you for the question.
Is there any other question? We have time for one more. I think there is one over there.
Hi, thank you for the talk. Can you comment about the sensitivity to the hyperparameters? You seems like that you choose 50, but there are some guidelines in choosing the hyperparameters of your algorithm?
Sorry, can you repeat that? The parameters?
The hyperparameter of your algorithm.
Yeah, the hyperparameters, the kappa, you mean?
Can you comment on the sensitivity to the hyperparameter selection of your algorithm?
Okay, I understand. So here there are a few like parameters. Since I mean all the parameters actually that we have, like we don't have many hyperparameters. Like the hyperparameter, for instance, the kappa is actually learned in the algorithm itself. And also, yeah, you're right. Like the number of effective dimensions perhaps could be learned. That's true, but in the end, like since you are limited by the number of dimensions that you can have, like it depends on your computation. So from that one, you can just try to choose the highest that you can go, and then like go with it, I guess. So thank you for the question. Thank you.
Is there any other last question? If not, we can proceed to the next talk. Okay, so we can move to the next talk from Aritra Mitra on linear stochastic bandits over a bit-constrained channel.
Thank you, Yannis. So I'm a new assistant professor at NC State, and this is work that I did while I was a postdoc at Penn with Hamid Hassani and George Pappas. Okay, so the main question that we're interested in today is how can an agent learn to take decisions when acting in an uncertain environment and in the face of information constraints? So if we pause and distill the key ingredients in this question, there's a control aspect because we're interested in decision making. There's a learning aspect because there's uncertainty. And there's also a communication aspect because we want to deal with information constraints. And if we zoom out and think about the big picture here, there's been a lot of work at the intersection of control and statistical learning theory in the last few years. What we want to do is add another dimension, that of communication. Okay, and the main agenda is to take the first steps towards developing a finite time theory for RL under communication constraints. Okay, and why do we care about this problem? Well, anytime you have more than one agent in your system, communication becomes an integral component. And this is more so the case if you think about large emerging ML paradigms such as federated learning, where you have tons of thousands of agents, and communication is indeed a major bottleneck. But almost all of the work in this FL space exclusively considers static optimization problems, not decision making. Okay, and that's the gap that we want to address. Okay, so with that as motivation, let me now set up the specific problem that we're interested in. And to do that, I'll draw inspiration from two canonical formulations, one in optimization and the other in control. Okay, so what I'm showing you on the left over here is perhaps the simplest abstraction that you can think of to capture communication constraints and optimization. So let's look at this model. We want to minimize a loss function f. We have a server and an agent separated by a channel. The server is going to send down a model to the worker at each time step. The worker will compute a gradient at the model. And then when it tries to send back the gradient to the server, it needs to do so over a lossy channel that can only support B bits transmission at each time step. So what the agent does is that it encodes the gradient using B bits, transmits it to the server, and then the server essentially just does gradient descent using the quantized gradient. And the typical question that you ask here is, how many bits do we need to achieve optimal convergence rates? And despite the seeming simplicity of this setting, a precise answer to this question was not known until recently. But the key thing to note here is that this is just a static optimization problem. There's no decision making here. Now, as soon as we turn our attention to decision-making problems, there's a very rich literature at the intersection of control and information theory, where you look at problems where you want to stabilize an LTI system, but the estimates of the state are transmitted again over a B-bit channel. Okay, and the question that you ask here now is, how many bits do we need to stabilize the LTI system? Okay, and an answer to this question was provided in this seminal work by Shekhar Tatikonda and Sanjay Mittar. And this sort of laid the foundations for the network control paradigm. But now if you think about this setting, this is a dynamic problem, but there's no uncertainty, because both the encoder and the decoder have complete knowledge of the parameters of the model, namely A and B. Okay, so by looking at these two settings, what we asked ourselves is, what's the simplest abstraction that we can think of that captures the three key ingredients: decision-making, uncertainty, and communication constraints? And what we came up with is this variation on the linear stochastic bandit problem. So let's go over this setting. Once again, we have a server and an agent separated by a channel. The agent is interacting with some environment. And what happens is that at each time step t, the server is going to send down an action AT. Think of this as a control input. And this action is selected from some time-varying action set script AT. The agent is just going to play the action in the environment. And upon playing the action, it's going to receive as feedback a reward or observation that obeys this linear observation model. Because if you look at this model, you have some Gaussian noise over here, and the reward is essentially an inner product between the action sent down, denoted by AT, and some unknown parameter theta star that lives in a compact set within RT. And the performance measure that we care about in this problem is cumulative regret. Okay, so if you think about this summation over here, it has two terms. The first term is the inner product between theta star and the action within the current action set that gives you the highest reward, because this is the action that's most aligned with theta star. And the next term is essentially the reward that you get by playing the action that you play. Okay, and the gap between them is the instantaneous regret suffered by the agent-server pair for not knowing the model a priori. And if you think about it, this is directly motivated by the setup, the control setup that I showed you a slide earlier, because we have essentially separated sensing and control by the channel. Now, when the channel is perfect, meaning that there's no loss in information, the best regret that you can hope for in a minimax sense is order d square root t. What we want to ask is, can we still hope to achieve the same regret when the channel can only support a finite number of bits? And if so, under what conditions on the number of bits? Now, why is this a non-trivial question? Well, if you think about it, the only way the server can take decisions is by using some knowledge about the environment. But the knowledge about the environment comes via the channel. But the channel, being lossy, is going to distort the view of the world as seen by the server. So this distortion is essentially going to lead to errors in decision making. And because this is a sequential setting, we want to ensure that these errors don't pile up over time, because that's the key challenge in this problem. So let's go over the contributions of this work. The first thing that we do is introduce a new algorithm called information-constrained linear CB. I'll explain this algorithm in a moment. And as a main result, what we show is that as long as the channel has ordered d bits capacity, our algorithm is going to give you the exact same regret that you'd get if the channel were perfect and at infinite capacity. Okay, so said differently, using just one bit on an average to encode each component of the model, you will incur no loss in performance. Okay, and this result essentially complements similar results that showed up for stochastic optimization, where if the gradients are d-dimensional, you need d bits to get optimal convergence states. Now, the next question that we asked ourselves is, if the action sets happen to have more structure to them, can we exploit that structure and hope to achieve optimal regret bounds but fewer bits? And the answer to this is yes. And to see that, what we did is looked at the basic multi-arm bandit problem, which is a special case of the linear bandit setting when the actions are the d-orthonormal unit vectors. Okay, and again, in this case, we came up with a new algorithm. But what we showed crucially in this case is that using just a 1-bit channel, you can get the same regret as you'd get with an infinite capacity channel. Okay, so that's the second main result. Okay, so in the time that remains, let me quickly go over the high-level ideas behind our algorithm that lead to these results. And let's start with the intuition for the encoding strategy. Now, we know that the unknown parameter theta star lives in some compact set theta. Okay, so a naive thing to do would be to just grid this set. Right? But if we just try to grid this set, this fixed set, the precision that we need to ensure that the errors don't pile up is going to be really high. In fact, we'll need the precision to scale inversely with the horizon t. But this is a terrible idea because if we do that, then the capacity of the channel needs to depend on the horizon t. And this completely rules out the possibility of considering long horizon problems, let alone infinite horizon problems. So how do we get around this difficulty? Okay. Let's denote by theta hat at the estimate of theta star at the agent, and theta at st the estimate at the server. Now, at the agent, it can just run a least squares estimator to maintain an estimate of the model. But the key idea here is that instead of trying to encode the estimate directly, what we try to encode is what's new in the estimate at the agent at time t relative to what the server already knows at time t minus 1. Okay, so this is essentially the innovation in the information. Why is this a good idea? Well, if the action sets are rich enough and we do enough exploration, it's easy to argue that the gap between consecutive estimates at the agent are going to decay. And as a consequence, we can also argue that the gap between the estimate of the agent at time t and the estimate of the server at time t minus 1, which is precisely the new piece of information, which is the innovation, that's also going to decay. Okay, so the idea would be to encode this innovation signal. But the challenge here is that this innovation signal for us is a high-dimensional random object. So how do we encode this innovation? Let's fix some epsilon between 0 and 1, and I'm going to generate two deterministic sequences, qt and pt. And my claim is that the innovation signal et is going to land within this ball of radius pt with high probability. And because this is true, it suffices to encode just this ball. And the key thing to note here is that because epsilon is between 0 and 1, qt and pt are decaying exponentially fast. What this means is that the regions that we are encoding are shrinking with time, and hence we are really investing our bits wisely by encoding very precise regions over time. And the main ingredient here is that we carefully exploit self-normalized martingale concentration bounds for linear bandits to design these encoder ranges. Okay, so that's encoding, but encoding is just part of the puzzle. It doesn't solve the entire problem because we need to still consider decision making. So unlike the standard bandit algorithm, our algorithm is going to have two separate phases. The first phase is a pure exploration phase where the server is just going to sample actions from the unit sphere. And the rough idea here is that this is an exploration phase that causes the agent to have very precise estimation of the model. And the next phase is going to be the explore-exploit phase, where at each time step, the server is going to decode the innovation sent by the agent, generate an estimate of the model itself, and then construct an elliptical confidence set that's centered at its estimate of the model. But crucially, this is an inflated confidence set. Why is this inflated? If you look at the radius of the ellipse here, it depends on the encoding error. It depends on the quantization error. So what we want is that the quantization error should decay fast enough so that the inflation in the confidence set eventually shrinks down quickly. And eventually, there's no loss in performance. Because that's precisely what we prove. And finally, the actions are taken based on a standard optimistic principle where you go over all thetas in the ellipse, you go over all actions in the current action set, and pick the action that maximizes the inner product. Okay, so in the interest of time, I'll skip the proof sketch, but I'll conclude by saying that we took some of the first steps here towards understanding the effects of communication constraints in RL by introducing a new bandit setting, designing new algorithms, and analyzing their sample complexity bounds. And as future directions, this opens up a really large space of problems to think about. How do we get lower bounds for these settings? How do we extend these ideas to the MDP setting and setting? Okay, so I'll stop here, and I'll be happy to take questions. And these are some related work in this space. Thank you.
Great. We have time for 2 questions. Any questions from the audience? Okay, I have a quick one. Do you have any convergence guarantees about the error in the estimate?
Yeah, so it crucially relies on the fact that if you think about the estimation error at the agent, it's going to be a Cauchy sequence. So the gap between the estimates is going to be small. And as a result of that, you can justify the encoding strategy. You can argue that with high probability, the innovations will in fact land inside the balls that we design. And that, that basically amounts to getting a sublinear regret in our setting.
This is more about the problem setup. What's the motivation for sort of having the agent transmit something related to the estimate of theta instead of, for example, transmitting a quantization of the reward?
Yeah, that's a good point. So this is motivated by some recent work in multi-agent RL where you don't want to send the actions or the rewards directly. You want to keep them private. Instead, you just want to sort of send model estimates. And in our case, the models are precisely the theta star, which is the unknown latent parameter. That's a good question, yes.
Is there any other last question? Okay, I think there is.
So I saw the theorem that says that above that number of bits, you can maintain that regret rate. I just wonder whether you have any feeling that you're optimally using the number of bits that you have when you're above that bound, because your result is about the regret, but not about optimally, let's say, using this number of bits in some sense. I wonder whether that is.
That's a great question. We don't have lower bounds. So in the case for the linear bandit setting, we don't know if order d bits is necessary. We just conjecture it might be, but it's probably not, because this gap between order d bits for the linear bandit setting and order 1 bit for the basic multi-arm bandit problem, this seems too large of a gap. I can tell you that if you want to get just the square root t dependence, you can do that with 1 bit. But you will have a worse dependence on the dimension. You will have a d to the power 3 over 2 dependence instead of d. So we don't know if, that's a great question.
Okay, great. So we can proceed to the next talk from Alessandro Abate on policy evaluation in distribution LQR.
Thank you very much. Hi, everyone. I'm presenting work that spans a team of 4 institutions. The main attribution should go to students Zifan and Yulong, who couldn't join us here today. So we're concerned with working with Markov decision. I'll just wait for the technical support, perhaps, to help. There you go. Thank you very much. So we're concerned with working with Markov decision processes, with general state spaces and action spaces, X and U. The dynamics are fully characterized by a transition kernel. It's a conditional probability distribution depending on the current configuration and selection of actions. We're interested in working with rewards that can be random variables depending on the current state and actions. Policies are also random distributions, random variables that depend on our current positions. And policies can be evaluated in a number of ways. For example, looking at what is the expected return across time. More formally, the expected value of the discounted additive return that the MDP incurs conditional on an initial state X. Now, it's very well known in particular in the area of reinforcement learning, that this expected return can be characterized as a fixed point solution of this celebrated Bellman equation. Now, perhaps less standard is a distributional view on this return, where, as it were, we drop all the expectations and work directly with the possibly random return. Now, it's been shown, and more recently, there's been quite a lot of work in this area in the distributional RL field, that this random or distributional reward, unsurprisingly perhaps, results from solving this fixed point equation, which newly should be emphasized that is a distributional equation, namely the right-hand side and the left-hand side ought to have the same distribution. It's intuitive that the latter interpretation should be richer than the more standard reinforcement learning interpretation in expected value, should carry more information. And pursuing this intuition a bit further with a trivial example, let's assume that we are in a static environment and we have a policy that incurs a fixed return equal to a half. And unsurprisingly, in this case, the expected return and the distribution return are the same. But as soon as we have a policy that is slightly random, namely, in this case, it incurs a small reward with high probability and a large reward with small probability, then it's clear that the distributional return gives more information than the expected one. So we want to pursue this distributional reinforcement learning direction, but of course there's some problems. This distributional return seldomly can be characterized explicitly. So it's common to try to compute approximation of this distribution, mostly with the categorical approaches that partition essentially the domain of the distribution of this return. Now, the question we're trying to address in this small contribution is it possible to analytically characterize, under some conditions, this fixed point solution for this random or distributional return? And our small contribution is in this direction is yes, and it can be done in the context of a distributional approach to the standard LQR problem. Now, let me give you a one-slide recap for the uninitiated on the very well-known LQR problem. Our MDP is now a linear dynamical system. The dynamics, the updates are linear, the input enters linearly, and there's additive disturbance characterized by IID random variables VT. The policy is a standard linear feedback that depends on this matrix gain K. So I'll index now an expected cost with this matrix K, and this is a cost rather than a return, but it's essentially what we saw before. We look at the expected discounted additive cost, which is a quadratic now cost of states and actions, given an initial condition X. And it's well known that these expected costs can be characterized by this Bellman equation, which, if Vt, the additive noise, is normally distributed, take this very simple, almost Platonic form, which is quadratic in this matrix P, which is the solution of this celebrated Lyapunov equation, plus an additive constant Q that relates to the variance of the additive noise. Now, let's look at a distributional version of this LQR approach. And as said before, we drop expectation here, and we work directly with the random costs now. It can be shown that this random or distributional cost solves a fixed point equation, which is very similar to the one that I showed more generally before, and then depends on the closed loop matrix AK and this newly introduced matrix QK. And now the question that we try to work out in our contribution is, what is this fixed point solution of this random Bellman equation in the context of this distributional approach to the linear quadratic regulator? And the answer to this question takes a bit of algebra, but boils down to assuming that the closed loop matrix is stable and writing out this solution of the fixed point equation, this random or distributional return, as this convoluted equation. It's a messy equation, but you recognize known terms. It's quadratic in the state. It depends on this matrix P, which actually is the solution of the deterministic Bellman equation that I showed before. There's quadratic terms in these random variables WK, which are IID and have the distribution of the additive noise, VK that I introduced before. And then there's cross terms, as expected. The issue with this characterization is, of course, that it's implicit. It depends on this infinite series. But thankfully, if you reintroduce expected value, this boils down to the standard LQR cost. Now, this is quite unwieldy because it depends on these infinite many random variables. So can we come up with an approximation of this characterized distributional LQR cost? And intuitively, this can be done just by truncating the infinite series to order capital N. And the question is, can we characterize the quality of this truncation? And the answer is yes. Let's look at the CDFs, the cumulative distribution functions of the original GK random return and the truncated one up to n terms. Under some standard conditions, the closed loop matrix being stable and the probability density functions of these terms WK that I introduced being bounded and satisfying this condition, we can uniformly upper bound the difference between the CDFs of the concrete original random returns and the truncated one, with a function that depends on the discounted factor gamma up to the nth power, where n is the order of the truncation, and a constant that is explicit and that depends on the parameters of the model, the matrix A, B, the matrices Q and R, as well as the variance of the WK terms, so sigma 0. So far, so good. Here's some experiments that show that these approximations are close to the so-called real distribution. This is a trivial example, one-dimensional. The additive noise is normal. It's not possible to characterize explicitly the random return in distributional LQR. So we use some Monte Carlo samples to obtain a surrogate of this return distribution. We use 10K samples. And we provide the distribution of the approximated random return GNK, which are the FN functions in the plots. For different values of the discount factor gamma, either small, equal to 0.6, or larger, equal to 0.85, which is the usual values that are by and large used in reinforcement learning. You'll appreciate that as gamma increases, you require more n's, more terms, to provide a closed approximation. We also notice that if the initial state x0 is small, then, which are the two plots on the left, then you get a distribution that is close to the chi-square one, whereas if x0 is large, you get distributions that are closer to being Gaussian. And this depends on which of the terms dominates the shape of these approximated returns. Now, so far, we've only looked at policy evaluation. What if we want to work with these policies? What if we want to improve these policies? Can we use our approximations in a policy synthesis problem? We've looked at this risk-averse linear quadratic regulator in a distributional setup. We've introduced this conditional value at risk, gk of x, which essentially looks at the expected value of the most pessimistic 1 minus alpha quantile of the distribution of the returns. We approximate the risk-averse error with the truncation introduced above and work out an algorithm which is a zeroth order policy improvement algorithm, very similar, resemblant to what we've seen earlier today and yesterday, that essentially initializes the matrix gain, then randomizes it with a random matrix UT that is which has a norm that is upper bounded by delta. We compute the approximated distribution return, GN, based on this randomized matrix, and the associated conditional value and risk, and then update the gain with a one-step update that follows direction UT with a step that depends on the differences between the current and previous conditional value and risk, and some parameters that depend on the dimension of the problem and on the norm delta that we've used to randomize the gain matrix. Here's some experiments we've run with a discount factor gamma equal to 0.6. We've used 2,000 steps in the algorithm and 10 terms for the truncation of the expected return, of which we computed the conditional value and risk. If alpha is equal to 1, which is risk neutral, we're able to derive the original matrix gain K, which corresponds to the LQR problem. If alpha is instead equal to 0.4, we get a different matrix gain K, which now is equal to minus 0.55 rather than the earlier value. And of course, we incur a conditional value risk that is larger than the one in the risk neutral case. So to conclude, we've shown that in a distributional approach to LQR, we can come up with an analytical expression of the random cost. It's rather unwieldy, depends on an infinite number of random variables. So we introduced a approximation that depends on truncating this infinite series and applied this approximation to a risk-averse LQR problem and shown that actually this approximation has tight bounds on its quality vis-a-vis the original random cost. We're currently working at extensions towards linear quadratic regulators, coming up with uses for model-free policy evaluation that actually use the approximation bounds, which is not what I've done in the experiments and in the risk-averse LQR case studies that I've shown. Thank you very much for your attention.
We have time for one question.
Hey, Alessandro, thanks for the talk. Just a quick question. Can you compute the CVAR of the approximated random cost exactly, or do you need to approximate that as well in the algorithm?
We need to approximate it. Okay. That's a very good way.
Yeah.
And we use a zeroth order policy gradient scheme because it's very, very hard to compute derivatives of it.
Okay. But I mean, the GT, can you compute it, or that's what you...
Yeah, the Gn we can compute. The CVAR of that we approximate.
Okay.
Okay, great. That was the last talk. Let's thank all the speakers again. And there is a quick announcement from Nick.
So just a quick heads up to everybody. I think it's raining outside right now, and so I just wanted to tell you a little bit about the additional space that we have in the building next door. In addition to Houston Hall, we also have the patio surrounding it that's reserved. And the building itself is free and open space, so feel free to walk into the building, both on the food court on the lower level and the kind of more lounge area on the top level if you're looking for places to sit. With that said, we're going to have coffee across the way. Thanks, everyone. Okay, welcome back from the coffee break as folks trickle back in and get seated. We're going to get started with our next portion of the program. Before we move on to our next keynote speaker, we're going to have another brief pause for a message from our sponsors, which is Mitsubishi Electric Research Lab. They're our other silver sponsor, and I'm just going to play the video that they provided us with that'll again tell you a little bit more about what's going on at Merle in terms of learning dynamics and control.
Hi, my name is Scott Bortoff, and I work at Mitsubishi Electric Research Laboratories in Cambridge, Massachusetts, and this is my 2-minute tour of Merle. So first, Mitsubishi Electric Corporation is a large Japanese conglomerate which makes lots of things: air conditioning systems, automotive equipment, factory automation systems, etc. Merle is a part of the corporate R&D organization, along with other larger laboratories in Japan. Relative to these labs, our purpose is primarily to do more fundamental research in signal processing, control, optimization, modeling and simulation, and artificial intelligence. Merle has a total of 57 researchers, of which 23, broadly speaking, work in the control area. So control is a big part of what we do at Merle. And the research is organized primarily in 3 different areas. So first, in control for autonomy, research is primarily on automated driving, mobile robotics, positioning and navigation, and various spacecraft technologies. In the robotics area, we research control algorithms, especially optimization-based and machine learning-based, for use primarily on existing robotic products that Mitsubishi Electric sells. And lastly, in the multi-physical systems area, the research is in modeling complex thermal fluid systems, primarily for the purpose of control design and optimization. Most of these problems are process control type problems, so there's a lot of MPC and various estimation type problems. There are other groups at Merle, including computer vision, signal processing, and communications, but they're a little beyond our scope. So lastly, I'd like to say that we host about 70 interns per year, so our population more or less doubles. These are graduate students from around the world, and we host also academic visitors who do sabbaticals at Merle. So if you're interested in Merle, please speak with me or contact me. Thank you very much.
All right, so I'd just like to thank Merle again for their support. And with that, I'm going to turn things over to Sam Coogan, who will be chairing the next keynote session.
It's my great pleasure to introduce Nadia Figueroa for the next plenary talk. So Nadia Figueroa is the Shalini and Rajiv Misra Presidential Assistant Professor in the Mechanical Engineering and Applied Mechanics Department here at UPenn. She holds secondary appointments in Computer and Information Science and Electrical and Systems Engineering and is a member of the GRASP Lab. She received a BS degree in Mechatronics from the Monterrey Institute of Technology in Mexico in 2007, an MS degree in Automation and Robotics from the Technical University of Dortmund, Germany in 2012, and a PhD in Robotics, Control, and Intelligent Systems at EPFL in 2019. Prior to joining Penn, she was a postdoctoral candidate associate in the Interactive Robotics Group of CSAIL at MIT from 2020 to 2022. Her research focuses on developing control and learning algorithms for collaborative human-aware robotic systems, robots that can safely and efficiently interact with humans and other robots in the human-centric dynamic spaces we inhabit. Her PhD thesis was a finalist for the George S. Geralt PhD Award in 2020, which is the best European PhD thesis in robotics, the ABB PhD Award, and the EPFL Doctoral Dissertation Award. Her co-authored work on multi-robot human collaboration was a finalist for the KUKA Innovation Award in 2017, Best Systems and Best Conference Paper Award, and winner of the Best Student Paper Award at the 2016 Robotics, Science, and Systems Conference. And so with that, I'll turn it over to Nadia to tell us about safety, adaptation, and efficient learning in physical human-robot interaction, a dynamical systems approach.
Thank you very much. Can you all hear me? Yeah. All right, well, first of all, thanks to the organizing committee for inviting me to give this keynote presentation. It's really an honor to have the opportunity to share my work, which is focused on developing controllers and learning algorithms for physical human-robot interaction from a dynamical systems perspective. So although I'm sure I don't need to convince this crowd about the importance of safety for robots deployed in the real world, I nevertheless want to stress how safety is even more critical in physical human-robot interaction scenarios. and how a robot that has no safety guarantees working in close proximity with a human can actually be very scary, like Aaron said yesterday. So I don't know if any of you have seen this headline a year ago. So I want to begin analyzing this incident that happened last summer when a chess-playing robot crushed and broke the finger of a 7-year-old boy during a match in a chess tournament. So after some Googling around, I discovered that this was the system that was actually playing against the kids in this tournament. So it was a 15-year-old refurbished industrial robot that was connected to a sensorized chess table with a strict turn-taking rules. So basically, the instructions for the users or the opponents were that the human should not make a move or enter the workspace of the robot when the robot is moving, right? So, and these are kind of like the typical turn-taking rules when you're playing chess. So let's see what happens. So the robot takes a piece from the kid's position D1, I think, and disposes it. So the kid, after the robot does this movement, you can see that he predicts the sequence of movements that will happen next, right? So basically, the robot will probably take the, oops, can we see it? Yeah. Take the bishop to D1, and then the kid was like, okay, if the robot is going to do this move, then I'm going to take my rook and take the bishop, right? So that was kind of like the prediction that the child did when the robot moved. But as you can see in the next couple of seconds, the kid actually broke the safety rules, right? Like the kid actually started moving his piece before the robot finished doing its move. So he broke the safety rules, the safety rule violation, so then let's see what happens. So then the robot just continued on, unaware of this, continues to place a piece and ends up in a deadlock between the gripper, the two pieces, and the kid's hands. And obviously panic ensues, right? You can see like all these adults coming in trying to release a kid from this deadlock. We can see the operator at the top trying to take over the control of the robot, disengaging the robot. So, okay, so you can say, we understand what happened, the kid just didn't follow the rules, right? And what's interesting is that this tournament, they have been using this robot for 15 years now. So they have been using this robot for 15 years in similar tournaments, and nothing like this had ever happened. So there was either a failure in sensing, a failure in planning, or they simply assumed that the human would follow the turn-taking rules and did not have a safety guarantee to avoid this situation. So we will never really know what really happened, but the takeaway that I want you all to have from this, and for me, is regarding the incidents, the assumptions that the users and that the designers of the system actually took in order for them to really deploy this robot in the real world, right? So let's break it down. So this is what I think the assumptions were, right? So the assumptions were that the humans are going to follow the safety rules. There will be no intentional physical perturbations from the human to the robots. They expect that the environment or the task that the robot has to follow is actually fixed. So with these three assumptions in mind, then we can actually control the robot with what I call a traditional trajectory or motion policy tracking framework, where we have a task specification that is given to some high-level decision-making layer. In this case, the chess-playing robot would be the strategy or the next move to make. Then this high-level decision-maker sends a desired target or perhaps some constraints or some waypoints encapsulated in this variable beta to a motion planner, right? And then this motion planner, typically what we do is then we try to optimize for some trajectory by optimizing a cost, right? So given the target and given these waypoints and maybe some time optimality constraints. So then the role of the motion planner is to generate this optimal trajectory, normally time reference trajectory. Then the low-level controller, the role of the low-level controller is to accurately track this trajectory, maintain the robot stable while tracking and perhaps rejecting disturbances or any external perturbations, right? So this is kind of like what I call the traditional way of controlling a robot. And a lot of people live in the area of the low-level controller and the robot, right? Because most of the times we really don't know. We have robots that maybe we don't know the dynamics, or there are sensor failures, things like that. So a lot of people live here. And a lot of the work that I see today and during these days are trying to come up with really fancy controllers, either for this block here or either for the motion planning block, right? And here, this dashed line, I make it in this way because this is really the only closed loop, kind of like feedback control inner loop that we have. And then sometimes we initialize the motion planner from from the start of the state of the robots, or if you use something like an MPC or receding horizon, then you kind of like restart this motion planner at different time windows, but there's really no feedback into that motion planner, right? So what I want to stress is that these assumptions are really completely incorrect for physical human-robot interaction. In fact, for physical human-robot interaction, we want the complete opposite of those assumptions. We should assume that the humans will never follow the safety rules. Even if there are rules in place, we will not follow them, right? Like we always take machines to their limits. Like we get tickets for speeding. Like we do all of these things we really abuse machines. So why are we not going to abuse robots? So it's really, we need to ensure that robots have these safety guarantees, even though the interaction or the task itself doesn't require a lot of physical interaction. And the other assumption is that there will be intentional physical perturbations from the human to the robot, and that the environment or the task will be dynamic, right? So if the assumptions change, then this traditional robot control, these objectives of like traditional robot control, I think this died for me. Yeah. So they no longer hold, right? So then we need to kind of like rethink what changes should we make in this robot control pipeline in order to achieve the correct assumptions for physical human-robot interaction. So this is what I'm going to talk for the rest of the presentation, outlining what are the changes that are needed, providing some solutions from a dynamic system perspective, while highlighting kind of like some of the contributions throughout my work. So as I said before, the first assumption is basically that humans just will not follow the safety rules, right? So we should always assume that. So no matter what the task of the robot is, if the robot is going to be operating a human-centric environment, the robot should always operate with fast and reactive control laws, no matter if the robot is static or if it's actually moving and doing some fast motion. The other assumption is that safety, so this is obviously kind of like a safety, fast obstacle avoidance, but right, fast collision avoidance is what we really care about. The other assumption is that safety is not always about collision avoidance in physical human-robot interaction, it's also about compliance, right? So the robot should really be compliant and kind of like passive and allow these physical perturbations from the human. And there can be different types of perturbations, right? So we can even classify them, like the video on the left here. You can see the robot is trying to do some form of inspection task, and I'm perturbing it at the target. So that's kind of like what I call an adversarial perturbation. Imagine a kid playing around with the robot and grabbing it, trying to see like what it does when it's moving it around. And then there could also be intentional perturbations, right? So perturbations that where the robot is doing a task and the human simply wants to come in and change something about the goal, change the object that the robot is manipulating, and so forth. So this is really something that's necessary, right? So right now I'm outlining kind of like what are these like the requirements that any robot, from my point of view, should have. Or the characteristics that any robot should have when it's operating in a human-centric environment. And then the other assumption is that the tasks are going to be dynamic, right? So there's not going to be like a static task where the robot just goes to a target or follows a static trajectory. They're really dynamic tasks. So like you should assume that tasks will be dynamic, which requires adaptive planning, right? So like the video on the left, where the two robots are adapting to the motion of a large moving object carried by a human, in this case myself, in order to perform this kind of like fluid handover. Or the video on the right, where a human is basically adapting or changing the target of this robot, and then it just kind of like adapts on the fly. So first it was going to pick up this box, and then it continues on when the target actually changes. So to ensure this level of reactivity and adaptability at the motion level for the robots, what we started working on with my PhD advisor, Ol Billard, who pioneered really this idea, is to represent the motion of the human and the robot as an autonomous dynamical system. Where x is let's say, is the position of the robot, x dot is the velocity, and f of x is this first-order differential equation that describes the evolution of the state variable x to a target x star, right? So if we represent this motion of the motion or the task of the robot as this autonomous dynamical system, we can actually ensure that we have these very nice like vector flows that are converging from these kind of like integral curves that are converging from anywhere in the state space to the target using tools from control theory, right, from Lyapunov theory. So basically introducing, assuming that we have a Lyapunov function and learning the parameters of this function f of x subject to this Lyapunov stability constraints. So to further exploit the inherent properties of reactivity, so it doesn't really only rely on having like this reactive and adaptive dynamical system motion planner. As I said before, compliance is also plays a big role in this. So as I was saying before, the traditional pipeline, this is the kind of like the traditional pipeline, and this inner loop at the bottom. At the right, this one normally runs really fast, right? Like between 500 and 1 kilohertz, depending on the robot that you have. The robots in the videos that I showed you are like KUKA robots or Franka robots, which are normally in that range. So what we propose is then, okay, so if we have this dynamical system motion planner, if we replace this trajectory optimization or this way of generating this trajectory through optimal control and instead replace it with this dynamical system-based motion planner, then we have actually another closed loop here, right? So first we have like this inner loop which runs really fast where the controller is basically trying to follow now the reference velocity that is given by this dynamical system. The role of the compliant controller is really to allow the perturbations, right? So for the robot to be compliant, or if the robot is already has some compliant mechanisms and it has kind of like some mechanical compliance, then the controller should be able to know how to deal with that, right? So basically we need this compliant low-level controller to allow for the perturbations, and as soon as the robot is perturbed from the path or from the velocity, from that tracking that reference velocity that the dynamical system motion planner is giving, then we still have this dynamical system motion planner in the loop, right? So like we know when the state changes, so then the dynamical system motion planner gives you the next integral curve or the next velocity from anywhere in the state space without having to replan at all. So and these can run really, really fast, right? So like I put 100 hertz in this loop just as like the minimum, let's say, frequency that we would want, but actually they can run at 1 kilohertz or even 2 kilohertz depending on how they're formulated. And we have shown that they are actually really fast because we have developed this controller where we, in fact, control these two manipulators with this dynamical system motion policy that's guiding the end effectors of the robots to match the position and velocity of this flying object, right? So, so this is really, really fast, right? So, like, actually, here the limit is the sensing. So, like, the bar is being sensed with this motion capture system at like 100, 150 hertz. So that's as fast as the robots really move because we're just doing like very simple prediction here. So just want to mention the feedback loops here. You can really use kind of like any flavor of compliant controller that you want, but just want to make it clear that's the type of compliant controller that we use, at least in these videos, is this kind of like tailored dynamical system impedance controller, where what we're doing is really trying to track that reference velocity that's given by this autonomous dynamical system f of x, right? So this controller only takes the current velocity of the robot, tries to match it to the velocity given by the dynamical system, and we construct this damping matrix as kind of like a gain, right? So to allow for the robot to follow this velocity, follow the velocity given by this dynamical system, but at the same time allowing perturbations from the human. So now, okay, so I laid out like how we should control the robots. So then how do we come up with these dynamical system motion plans in the first place, right? So how do we come up with these dynamical system motion plans, and how do we enforce explicit safety, like really fast collision avoidance, like in the videos that I showed at the beginning? So I'm gonna start first with explaining how we get these dynamical system motion policies, and this is through learning from demonstration. So there are many ways of doing this, but also another objective that I feel that robots should really have is efficient learning, right? So being able to learn really fast from a couple of demonstrations from the human, what the task or the skill is that the robot should follow. So the pipeline is quite simple. You kinesthetically demonstrate the task to the robot. We collect those trajectories from the end effector. We fit these autonomous dynamical systems from these trajectories, and then we deploy them on the robot with these low-level controllers that are compliant. So if the robot is not perturbed, it's going to perfectly follow the trajectory that was demonstrated, but if it's perturbed, then it's going to follow kind of like the integral curve that was shaped by this shaping algorithm. So, this problem of learning kind of like this function x dot equals f of x can be seen as a very simple regression problem, right? Like, so we can say, okay, so let's just use any machine learning algorithm to learn this function f of x. And we could do that, and people do that, but I wouldn't recommend it, because we cannot really ensure, without imposing any type of constraints of stability or convergence, we cannot really ensure that the robot will not diverge or will not end up in some regions in the state space like spurious attractors, right? Because we're not really introducing any type of stability guarantees if we're just using like an off-the-shelf machine learning technique. So here, for example, I have an example where I use Gaussian process regression to fit these trajectories to a dynamical system form. So by doing regression, so the input is the position, output is the velocity, very simple. We get very accurate reproduction from the initial conditions, right? From the initial states, and very close to the data that we demonstrated, we get very accurate reproduction of the trajectory. But you can see here we have these spurious attractors in the middle, and then at the target doesn't even reach the target. It kind of like passes through the target and then diverges, right? So if we deploy something like this on the robot, and the robot is perturbed, because we're assuming that it's going to be perturbed by a human or by some control error or anything else, then it will diverge, right? And then this will cause instabilities, and it will cause unsafe behavior. So by introducing stability constraints onto these dynamical systems, then we're kind of like implicitly also achieving safe behavior. So then, okay, let's try neural network, which is what everyone is very fond of. So we use a neural network, and same, right? So it reproduces very nicely the trajectory from the initial positions, very close to the trajectory, but we have these spurious attractors, and in the regions outside of the data, far from the data, we don't know what's going on, right? Like it might diverge. So of course, we said, okay, so what can we do? So like we can actually impose global asymptotic stability conditions on these models using Lyapunov's direct theorem of global asymptotic stability, right? So Aaron already introduced kind of like Lyapunov and control Lyapunov functions. So these are like the more standard Lyapunov function. It's not control Lyapunov, but it's a Lyapunov function. So basically we know that if there exists a dynamical system for a function f of x, and then the time derivative of that Lyapunov function is negative, definite, anywhere in the state space except at the target, then we know we can ensure global asymptotic stability, right? So basically what's going on is saying like this function f of x, our dynamical system, should the Lyapunov function corresponding to it should be non-increasing all along the trajectories of our dynamics. And this is just kind of like a very simple geometrical representation of this, right? So we have the gradient of the Lyapunov function and the direction of our vector field, and basically the condition states that the vector field should always kind of like point towards the lower level sets of the Lyapunov function. Like that's really what this means geometrically, right? And we know from textbooks that we can easily construct a quadratic Lyapunov function for a linear system, right? So if we have a linear system like this, and we can find a P matrix that's positive symmetric definite, then we can actually prove that our dynamical system is stable if we kind of like have these conditions, right? Of that the eigenvalues of this matrix, A transpose P plus PA, are negative. So we took that idea and said, okay, so what if we represent this nonlinear trajectory as a mixture of linear systems? Since we know how to stabilize a linear system, could we make a mixture of linear systems stable, right? So we introduced this idea of basically having a mixing function. So this is generally from control theory, a linear parameter bearing system, a linear parameter bearing dynamical system, where we have these separate regions in the state space that actually represent exactly a linear system, right? So like in this S shape, we have, let's say, 5 linear systems that are fitted very nicely on the trajectory, and that can perfectly kind of like reproduce these linear a linear system. And when mixed together following these constraints, so basically this mixing function, which is kind of like the mixing or weighting of all of these linear systems, should sum up to 1 and should be between 0 and 1. So basically what this mixing function is saying is kind of like an activation, right? So like when gamma 4, let's say, is very high, with a value of 1, then dynamical system 4 is the one that's acting, and it's shaping our dynamics, our vector field, and so forth for each of them. So a very natural way of representing this gamma function, this mixing function, is based with the Gaussian mixture model, right? Because it's basically a Gaussian mixture model. It's a mixture, weighted mixture of Gaussians, and that can very nicely represent a trajectory like this one. So what we do is we use the a posteriori probability of a Gaussian mixture model that's fitted on these trajectories as our gamma function. So basically when the robot is, let's say, near region 5, then gamma 5 is going to be almost 1, and all the others will be 0. And then in between, they will all have some values that sum up to 1. So then the entire mixing function will always sum up to 1. There will always be like one, the dynamics, or a summation of dynamics, mixture of dynamics that is guiding the robot. So that's how we how we generate this gamma function. So then what's left is, okay, now let's learn each of these linear systems. How do we learn each of these linear systems parameters? And so what we can do is we basically formulate a semi-definite program where what we do is, the objective is we try to minimize the reproduction error of these trajectories, and we impose these Lyapunov stability constraints for each of these linear systems. So the assumption is that there's a single Lyapunov function that that is basically, so basically each of these linear systems shares the same Lyapunov function, and they all share the same attractor, right? So we know that if we have that same linear, same Lyapunov function, then we can derive these kind of like stability constraints for each of the linear systems. And for example, the first one basically is ensuring the dissipation of energy of the dynamics, and the second one is the convergence to the attractor. And this can be a non-convex semi-definite program if we don't know the P, like if we don't know the Lyapunov function beforehand, but it's solvable. There are solvers that can solve this really fast, actually. But we can actually we can even estimate like a good guess of this P matrix of the Lyapunov function by optimizing it before learning these linear systems, such that by solving this optimization problem that basically minimizes the number of data points that violate the Lyapunov condition. So we run an optimization to get like the best value of P that we think fits our trajectories. And then if we go back to this optimization, now this is convex because now we know the P. So all we need to do is learn all of the A. So this is basically a convex optimization problem, and we can solve it super fast, which is nice. So of course, this is all really cool, but the caveat is, how do we get these separation? How do we get this state partitioning of the Gaussian mixture models, right? Like how do we put these linear systems very nicely fit in linear parts of the trajectory of the demonstrations? So to ensure that, and the number of linear systems as well, right? So we also proposed an approach for this. So basically a Bayesian non-parametric Gaussian mixture model, where we do sampling to kind of like estimate the optimal number of Gaussians that are necessary for trajectories using a similarity metric that we call physically consistent. So that also takes into consideration not only the locality, so basically the measure of distances between the points on the trajectory, but also the directionality, so that each of these points on the trajectories, their direction or their velocity are pointing in the same direction. So by doing this, we get a very nice clustering of our trajectories, and we ensure kind of like what we call physically consistent fit to our Gaussian mixture models. We infer the optimal number of Gaussians, K via sampling, while ensuring a physically consistent fit. So, this approach actually is the one that we use to learn almost all of the systems that I showed in the previous videos from when I started the presentation. And here you can see, and actually we have it running in a permanent exhibition at the MIT Museum. And here you can see that we trained this museum facilitator to actually teach people how to teach a robot like a trajectory, and then you can see very quickly, like in a minute, like after giving the demonstration, you only needed one demonstration or two. The robot learns runs this optimization that I laid out. Here they're giving the demonstration. Now she's gonna click on the GUI that we made for her, so that the optimization is running. So that then the robot will actually learn the trajectory, and then you'll see that in very super efficiently, like it already learned the trajectory that was demonstrated, it reproduces it, and it's also safe, right? So like it's running this compliant controller, so they can play around with it, they can perturb it. So this demo is actually running kind of like 24/7 there at the MIT Museum. So if you're ever there, go there, play around with it. If it doesn't work, let me know so we can fix the errors. So as I said before, here it's already like we're already achieving very efficient learning with a couple of demonstrations, right? Couple of demonstrations, we can learn like these kind of like complex skills in a very efficient way, 1 minute. So in the ongoing work, we're actually improving with this mixture model estimation by introducing a directionality-aware mixture model, kind of like parallel sampling for these efficient dynamical systems. And in this plot simply shows kind of like the PCGMM is like that previous sampler that I showed, and this new one, which we call DAM, directionality-aware mixture model, is like orders of magnitude faster. And the way that we did it was by leveraging distance measures in the Riemannian manifold. So instead of using this kind of like separate similarity metric, we're actually using a metric on the directional information of the velocities. So we don't need to have any kind of like separate metric that's biasing the clustering. And then that way we can actually have this kind of like hybrid sampling scheme that combines Gibbs sampling and split merge proposals to facilitate almost real-time learning. So we almost in a second, we can actually learn now these motion policies. This work is currently under review, so I cannot go like, I'm not gonna go really deeper into that, but I just wanted to mention it as is work from one of my master students here at Penn. So one of the things that is interesting is that, of course, if you notice, like you give one trajectory and then the robot just learns kind of like a static representation of that vector field, right? So if something changes, if the target, let's say the tunnel changes or some geometric, let's say constraints or via points that the robot should actually pass through change in the task, then these dynamical systems do not adapt because they're just learned from like very egocentric just from the trajectories, right? So then we started working on this new approach where we say, okay, so then we don't only need the trajectories and the target, but also let's take into consideration this variable beta, which basically takes into account kind of like waypoints or constraints in for our dynamical system. So what we did was, this is also ongoing work, it's currently under review, so I'm only gonna show kind of like the results. So we can achieve actually task transfer without giving any new demonstration. So here, let's say we have these two dynamical systems. that were learned from a single demonstration. The top one has a geometric constraint, which is this kind of like green polygon, which is kind of like, let's say, a peg that the robot should go and insert. And then the bottom one, we have kind of like 2 geometric constraints. So if the geometric constraints change, then what we do is we basically transfer kind of like the Gaussian mixture model, the parameters to this new change in the geometric constraints. And as you can see here, we're kind of like morphing or creating this kind of like elastic dynamical systems that are transferring to different tasks without having to give any new demonstrations, just by introducing kind of like the geometric descriptors or constraints that we are introducing into our motion policies. And here we can see a video of this in work. So basically here we're teaching a robot how to kind of like insert a book into a bookshelf. We gave one demonstration, it reproduces that same demonstration. Then we shift the bookshelf closer to the robot. The robot adapts to that change without having to give any demonstration. We shift it again. It adapts and it achieves the task. And then we shift it again but now with human demonstration. So it has both that reactivity, it's adaptive, and it's also adaptive at the task level, right? So like it's basically adapted to these changes in the task. And also in a completely different rotation and translation of the target as well. So that was one of the ongoing works that we're working on here at Penn with one of my PhD students. So now that you saw that, like, okay, we can achieve really cool behaviors with these dynamical system motion planners, what if we model the motion plan as a controlled system, right? Like, so here we're assuming that this planner is an autonomous dynamical system, but it's kind of conservative in the sense that we assume that there's a single target, so that limits the expressivity or the complexity of the trajectories that we can actually demonstrate or reproduce. So what we did was this work with, in collaboration with Nick Matney and his PhD student Farhad. So then we actually, we modeled these motion policies as a control system now, right? So like the whole idea is that we learn kind of like an unstable trajectory with a neural ODE, and then we solve for a virtual control input to actually stabilize this system. And as you can see here, we kind of like demonstrated a task where the robot is kind of like wiping this the body of a human, following this very periodic kind of like trajectory, which the other type of dynamical systems really can't handle because there's no targets, right? It's just a trajectory. And here we have another demonstration of this same system, reproducing kind of like this periodic motion for the pen. So that's kind of like the ongoing work that we're doing here at Penn. So now what about enforcing explicit safety, right? What about enforcing explicit safety constraints, which is in this case collision avoidance? So obstacle avoidance through dynamical system is very simple to do, actually. So given, if you already have, let's say, a global autonomous dynamical system, some years ago, my PhD advisor together with Mohik Ansari proposed this approach where we basically modulate, if we have a representation, a continuously differentiable representation of the obstacle that you want to avoid, what we do is we construct this modulation matrix to kind of like reshape the vector flow. So it scales the velocity and reshapes it around the obstacle. So this, which we call the gamma function. So this gamma function is kind of like monotonically increasing radially from the object following these properties. So it must be monotonically increasing. It should be equal to 1 at the boundary and continuously differentiable, right? So and obviously you can see kind of like it's kind of like increasing following the boundary of the obstacle. And it's actually very similar to a barrier function. So it has exactly the same characteristics as a barrier function. Once I arrived here at Penn and I started talking to my colleagues about this approach, they were like, so what's the difference with a barrier function? And I said, I don't know, but let me figure it out. So one of my PhD students actually did a very nice work in her first year to figure out like what was the difference, and actually there is no difference. So like this boundary function is actually a barrier function. It was just a different formulation of it, kind of like more from a geometric geometric perspective. And we even have a way, so the way that we construct then this modulation for obstacle avoidance is very simple, right? So what we do is we take the gradient or a reference direction that's pointing outwards from the boundary. In this case, if we have the continuously differentiable function, then we can easily take the gradient. We use that gradient to construct an eigenbasis for this modulation matrix, which is creating kind of like an eigenbasis to represent the velocity that's going towards the boundary of the obstacle, kind of like in a normal direction and tangent. And then the eigenvalues here, this eigenvalue matrix, what it's doing is kind of like shrinking the velocity and bleeding velocities onto shrinking velocity on the nominal direction, on the normal direction, and shrinking and bleeding it to the tangent directions. So we actually proved, inspired by one of Aaron's papers, where they proved that artificial potential fields is actually a special case of CBF. We know that this modulation approach is actually a generalization of artificial potential fields, but by getting rid of all of these local minima, except for a single local minima. So then we also have a proof that we show that this modulation approach is actually a special case of a CBF, but it's currently unpublished. We're going to release it soon once we finish the comparisons, but we have very nice results showing that basically using this kind of like construction of the eigenvalues and taking the normal direction and the tangent, we use those geometric kind of like parameters to construct the gamma function, and then that's how we get the equivalent between CBF and DS modulation. So another improvement that we made on this approach is that, so as you see here, so this works, and there's proof for this type of approach for convex obstacles and for star-shaped obstacles, but not for arbitrarily shaped obstacles, in the sense that we can prove that the robot will never penetrate the obstacle, but there will be local minimas, simply because it's a very geometric approach. And we actually also proved that CBF also has this type of let's say, this pathological little problems where the gradient or the direction of the H barrier function is going in the opposite, is collinear to the nominal velocity or to the nominal direction of your nominal system. So what we did in collaboration with PhD students at MIT, advised by Julie Shao while I was doing my postdoc there, we were like, okay, so what can we do to actually represent like arbitrarily shaped obstacles like humans, like fully kind of like concave enclosed environments around the robots. So what we did is we proposed this kind of like sample-based gamma function, which is more or less a gamma field that is given a set of points. Imagine if you have a point cloud or points from LiDAR, you can actually, what we're doing is fitting these kind of like radial basis functions subject to some constraints, and actually this function is not just continuously differentiable, it's twice continuously differentiable. So we have continuous gradients, and we also have a Hessian that we can use to kind of like circumnavigate these really concave obstacles. So we show, so here we have a paper on the review at TRO where we show that this modulation approach with this new kind of like a representation of obstacles can do very nice obstacle avoidance in kind of like completely constrained environments, and obviously in fully reactive dynamic environments. In this case, we're tracking all of these objects using motion capture system and kind of like sampling points on the objects and the obstacles, and then creating this boundary function, which is this red kind of like sign distance field that you're seeing, kind of like this shape, and it's, as you can see, it's kind of like updating in real time, right? So the obstacles are updating 100 hertz, and the robot is really, really fast, like updating and being reactive to this. So, from this, you can see kind of like how interesting it is. Like if we have a really good representation of our environment, and it's really fast or efficient to generate or to infer, then we can easily have very fast like obstacle avoidance, either using control barrier functions or using this type of like modulated dynamical system. But all of this is obviously kind of like in the state space, kind of like in the Cartesian task space of our robots. So a few years back, and it's only really ensuring the safety of the human, right? Like not necessarily kind of like safety of the robot in terms of self-collisions or collision with the environment. So a few years back, in this work co-authored with Sina Mirasavi, we were like trying to figure out like, okay, what happens if you have two robots that are working together, and then we have this inherent passive or compliant controller, but we push one robot towards the other. So they should be able to avoid each other, right? Like if we're controlling them kind of like in a centralized system, then they should have this very fast self-collision avoidance kind of like controller running in the low level, even if it allows the perturbations from the human and this compliance. So what we did is kind of like inspired by these functions that we are representing obstacles in the environment. We thought, why don't we come up with this continuously differentiable function that represents the boundary to collision in joint space, right? So like basically we come up with another gamma function where the input is the joint state of the robots, in this case two multi-degree of freedom robots, and we have these constraints on these implicit distance functions in joint space, right? So in the colliding configurations, less than 1, on the boundary equal to 1, and free configurations positive 1. So it's basically a barrier function in the joint space. So it's obviously super difficult to generate this mathematically or come up with an equation of this in joint space. So this is where we can use learning, right? So like if we can sample the collided and non-collided configurations of a robot, then what we did was like, let's say, okay, let's learn the boundary using learning, right? We sample all of the colliding and non-colliding configurations of our robot in the state space. We try to learn the boundary. We figure out how to learn this continuously differentiable boundary of the robot state space with these properties that we want. And the very first use of this that we did was actually computing this constraint using for a QP, so for an inverse kinematic solver, so a low-level controller. So the whole idea is that if we learn this self-collision avoidance function in joint space, then the gradient of this function is basically giving us the repulsion direction of where to go if the robot is going close to those boundaries, right? So let's say the robot is in joint space moving around, so like if we impose this constraint to not penetrate the collision boundary, then what it's going to do is just going to try to like repulse from that boundary and just try to bring the robot back to free configuration space. So this is an example of that, of such an inverse kinematic solver running in real time at 500 hertz, I believe this was running, yes, yeah. And here the two robots are tracking kind of like the markers of my colleague while trying to avoid colliding with each other, right? So then what we did is we extended this works. They said, okay, so we can do that. We can learn self-collision avoidance boundaries for a single arm, for multiple arms, and also for a humanoid robot, right? Because all we need to do is kind of like sample efficiently this boundary where the robot is in self-collision and not in self-collision. So this is kind of like showing how this self-collision avoidance boundary function is evolving when we use it within an inverse kinematic solver. The orange point is kind of like the actual point, the state of the robot. And as you can see, we can avoid doing self-collisions for the robot as well. So this is a really this is a critical problem for human robots when you're trying to grab something from the ground. Normally it goes directly to that crouching posture because it's kind of like just trying to minimize the joint configuration. So here is an inverse kinematics. The first one was without the collision avoidance constraint, and the second behavior was with collision avoidance constraint. And you can see it kind of like finds very nicely that posture to avoid collision without really doing any type of high-level control, anything like that, just by introducing that constraint of self-collisions. So this is the video of the robot in real time. And so then the last thing that I wanted to show is like we said, okay, so we can learn this self-collision. So what could we learn this self-collision? An external collision function from joint space where the input is the joint space of the robot and the output is a distance to a collision of points in 3D space, right? So that's always the issue of figuring out how to represent obstacles in task space, but and putting them in joint space. So what we did is we sampled the joint space of the robots, gathered all of this data. We fit a neural network to it, and we learned this external collision function in joint space, basically. So you can see kind of like this function is telling us like what's the distance to collision to a robot from anywhere on its body to a point in task space. This work was led by Michael Koptev, who's a PhD student at EPFL. The paper is so this paper for learning the boundaries is actually published at RAL, but then we used it in a real-time collision avoidance using that modulation approach directly in joint space. And here you can see the results. We actually just submitted this paper to IJRR, and Michael just defended his thesis a couple of days ago with very positive results. So here you can see kind of like real-time collision avoidance in joint space. We're using the motion capture system to kind of like track the points, these rigid bodies on his body, and then fitting a whole bunch of spheres on his body. And as you can see, it's super reactive, right? Like it's capable of getting out of these local minima. Here what we're doing is we're extending the modulation approach by having two layers. Having a layer that's running the real-time modulation, the kind of like the dynamical system feedback controller that's modulating using this boundary function. And then we also have a MPC controller that's running kind of like at a lower frequency, trying to find where the local minimas will happen and then start reshaping. So very similar to kind of like one of the last works that Aaron presented yesterday. So I think I'm going to end here with the work. So I just wanted to mention that. So a lot of this we actually published a textbook where we wrote about all of these approaches of how to use dynamical systems to represent motion policies, how to learn them, how to create adaptive and reactive behaviors for control, together with my PhD advisor, Billard, and Sina Mirosavi, who's my colleague and co-author in a lot of my papers. Before ending, I would like to mention all of my collaborators, PhD students, postdocs that I work with that are co-authors in a lot of the papers and works that are presented today. Obviously, my supervisors, Billard from EPFL and Julie Shah from MIT from my postdoc. And my group, with this picture we took actually 9 months ago. So for those of you who actually went to the tours, there's much more robots and there's a lot of cameras in my lab now, like after 9 months. And also I want to mention Farhad and Nick, who are collaborators in one of the work that I presented today. So thank you very much for your attention.
Great, thank you very much for the excellent talk. So with that, we have a few minutes for questions, if there are any questions from the audience. Yeah, there's a question up front here.
That was so cool, Nadia. Thank you. Can you tell me a little bit about how you're thinking about incorporating perception-based models in here? How does vision and sensing play a role in this whole pipeline that you developed?
Yeah. So actually, I have several projects right now in the lab that we're trying to see like what happens when we use real kind of like off-the-shelf sensors, right? In all of the videos that you showed, we're using this super expensive motion capture system that tracks the objects, that tracks the humans at 100, 200 hertz. So the frame rate, the sensing is really fast, so that's why we can get this really fast and reactive behavior, right? But as soon as we try to use, for example, a RealSense camera, the maximum that we can get is 90 hertz, if we can actually achieve that, right? Like normally they run at 30, 60 hertz. So there's a big gap between like the frame rate that we would get from these onboard cameras and the reactivity of the controllers. So we are exploring kind of like different ways of how to get like very efficient, like representations of these kind of like boundary functions from sparse sensor data, using exploring. There have some students exploring NERF. Trying to see like if we can get these sign distance functions or distance functions from like an RGB image, which would be much faster than trying to reconstruct the 3D point cloud from like the 3D reconstruction of the camera or from LiDAR. So yeah, that's definitely an issue, and I find it very interesting to figure out. So in that case, we would need some form of prediction from my point of view, in order to ensure that at least we have kind of like the if we have a very noisy measurement of where the obstacle or the human is at this time, at least we have some estimation of where it will be in the short horizon. So basically doing kind of like an MPC or predictive control on the human or on the obstacle so that the robot can be very reactive to like that prediction. Right, so and there's many ideas that we're also exploring, like maybe using kind of like reachability analysis as well on the obstacles. And one thing that's interesting is that how to handle uncertainty, right? Because in all of these controllers, like we assume that the state is known. There's no noise in the system. There's no noise in the measurements of the obstacles. But I have another student that's analyzing this. Like, what if simply the target, like the attractor is super noisy? Then these reactive controllers are going to start kind of like they're bounded, like they're not going to diverge, but they will end up going to kind of like a region around the attractor where they're just going to oscillate around it because of the noise that's coming from the measurements. So we're coming up with ways of like how can we come up with like virtual control inputs to stabilize the stable dynamical system, but from the point of view of stabilizing it using taking into account the noise. If we can estimate somehow the noise or some bounded noise from the measurements, how to stabilize the system when it's being disturbed by that. So yeah, there are many problems with that. That's kind of like what a lot of my students are exploring right now. Like how can we because obviously we cannot assume that we're going to have these super fancy motion capture systems in everywhere. Right, so we need to figure out how to use sensing and low-cost sensing. So then that's where the gap really lies. And yeah, so I'm currently really interested in figuring out like how to solve that, how to deal with uncertainty in general. Yeah. Yeah. There's a question.
There's another question way over here.
Hello, thank you for the wonderful talk. I was curious whether you have any thoughts regarding regularization for optimality with your demonstration stuff, because like it seems likely to me that there may be some scenarios under which humans might be physically incapable of demonstrating like a proper trajectory for a given task, and I'm curious how you think about interpolating between that and what might be computed more optimally for that particular task?
Yeah, that's a very good question, and indeed that's a really interesting problem, right? Because so by using kinesthetic teaching, I'm kind of like assuming that at least the trajectories that are being demonstrated are feasible for the robot in terms of their kinematics, because we're using gravity compensation, so the robot should be able to do it. But it could be that the human is demonstrating it in a suboptimal way just because of their own kinematics. And I didn't show a video, but so most of the videos that I showed is just one human demonstrating to one robot. But when you have two robots, actually during my PhD, I taught a robot to do like a bimanual peeling. And I had to kind of like train myself to actually grab the two robots with the two tools and figure out how to teach it. So I mean, one way that we're exploring currently in my lab is to construct like a teleoperation using gloves, and so that we can kind of like teleoperate the robot so that the human is more comfortable. And that teleoperation requires more of a shared control architecture as well. So that's one way of doing it. But the other way that's also interesting is try to do something like a self-learning approach where maybe the human gives a demonstration and then the robot tries it on its own, like in simulation, tries to kind of like reproduce it and evaluating if this is if this is really the optimal demonstration for that the robot can actually achieve, or if this demonstration is coming with the limitations of the human, when this is kind of like the correspondence problem, like but at a different level. So yeah, so there are many ways of solving that, but indeed that's an issue. So when you're just teaching one arm, it's easy, but as soon as you go to bimanual, then it gets really difficult. Yeah, and that's where we need to figure out better ways of teaching, better ways of, or even how to, like get demonstrations maybe from video directly, but that's a big problem as well, the correspondence. So yeah, so as soon as you try to teach a more complex robot these tasks, then it becomes more difficult, yeah. But it's an interesting problem, indeed. Any other questions?
Okay, great. Yeah, there's another question in the back.
Thank you for the talk. So I was curious about repetitive tasks. For example, turning a gear, where now in your vector field, you do have some cyclic, some cycles. So how do you actually tackle those type of problems from a safety perspective?
So if I understood correctly, your question is like, how do we deal with these kind of like cyclic or like limit cycles or periodic tasks like wiping, like a spiral or things like that? So with the first approach that I presented that assumes that it's an autonomous dynamical system following this Lyapunov function with a target, it's not possible to do that. It could be possible. There's one way, there has been one paper that has done that, but what you can do is basically transform the coordinates, kind of like polar coordinates, and then you have a limit cycle, and then you can impose like the stability constraint on that limit cycle, right? With the polar coordinates, it's really easy. But the work that Farhad did was basically not assuming that we have an autonomous dynamical system. It's actually a control system. So we actually learn a reference trajectory, which is this cycle. So we learn the reference trajectory that could be a spiral or that it could be some periodic task. But that reference trajectory, it's unstable. Like there's all these instabilities, and when we use a control Lyapunov function to actually try to minimize the error and alleviate all of these kind of like spurious attractors that would happen in the periodic cases. So for the periodic cases, we actually use like a controlled system approach where we have an unstable system, learn with a neural ODE, and then we control it using this virtual input.
Okay, great. I think with that, we should probably take the rest of the questions offline. So let's thank Nadia again.
Thank you very much.
And I'll let Nick.
All right, thanks, folks. We're going to head over back to Houston Hall for lunch, and then there'll be a poster session after that, and then we'll reconvene back here at 2 o'clock for the next oral session. Thanks, everyone. a teaser video from our final sponsor, Raytheon Technologies. Okay, let me take this opportunity to thank our sponsor Raytheon again for their support. And with that, I'm going to turn the floor over to Nikolai Atanasov, who's going to be presenting our next keynote speaker.
Hi, everyone. It is my great pleasure to introduce our next speaker, Professor Tamer Bashar. Professor Bashar is the Swanlund Endowed Chair Emeritus at the University of Illinois, Urbana-Champaign. He's also the Professor Emeritus of ECE and a research professor of CSL and ITI. Professor Bashar has been with UIUC since 1981 and has served in a number of roles. He's been the director of the Center of Advanced Study. He's been an interim dean of engineering. He's been an interim director of the Beckman Institute. And Professor Bashar is a member of the US National Academy of Engineering, as well as of the American Academy of Arts and Sciences. He's a fellow of the IEEE, of IFAC, and of SIAM. He's served as the president of the IEEE Control Systems Society, the president of the International Society of Dynamic Games, as well as the president of the American Automatic Control Council. He has served as the editor-in-chief of Automatica for 10 years, between 2004 and 2014. Professor Bashar has seminal contributions in many areas, including control, systems, communications, optimization, networks, and dynamic games. His work has been recognized by the highest distinction in many of these societies, in IEEE, CSS, IFAC, the American Academy, the American Automatic Control Council, and ISDG. Some of his awards include the IEEE Control Systems Technical Field Award, as well as the Wilbur Cross Medal from Yale University. It is a great pleasure to have Professor Bashar today, and he's going to tell us about consensus and dissensus in multi-agent dynamical systems with learning.
Good afternoon, and thank you very much for this generous introduction. So this talk will bring a game element to this conference, and we'll see how that will come in within the context of consensus building and also dissensus, and I have to make clear what that stands for. And there will be some learning element as well as time allows. So the development of opinions and evolution of opinions really has been a topic of interest to many disciplines, all the way from social sciences, political science, and math, and engineering as well. So in the simplest form, you can formulate consensus building as on a graph topology, you have nodes, and nodes could be individuals, and this could be the space of opinions, actually. And individuals interact with others, and they maintain some opinion on some subject or on a variety of subjects and topics. And then they, if they like the opinion of their neighbors, then they could try to get closer to that opinion. And if some of their neighbors have opinions which they disagree with, and they try to stay away from those and try to maintain a certain distance. And we see this in the political arena in particular. So we can have nodes which represent these opinions of different agents, interact with neighbors. Now, if they try to get closer to the opinions of others, so that's what we call consensus. And if they want to maintain a certain distance with others because they don't agree with them, and this is what I would call dissensus. And the question is what sort of a mathematical model we can come up with which will accommodate and capture both consensus and dissensus within a single large-scale decision-making formulation. And definitely there is evolution of opinions, so there is it's a dynamic process. And the individuals have different objectives, generally, and they act according to those objectives. And because of the disalignment of the objectives, it's the only way, in my opinion, to approach this problem is a game theoretic one, and particularly using dynamic games, because it's a dynamic evolution of opinions. And so the game theoretic formulation has to build into the model the objective functions of different agents, their preferences and attitudes toward others in different populations. And so we generally, in such scenarios, in such settings, have a very large number of agents who interact with each other, either directly or through several hops. And this leads to sort of an asymptotic analysis of any game theoretic solution concept. And this is what has emerged as a mean field game paradigm in the last, 15 years or so. So I'll be introducing, make a digression first from consensus building and talk a little bit about the current state of affairs in game theory, particularly the mean field games, and how one can go ahead and obtain acceptable solutions. So the outline of this talk, as I indicated, will be a high-level introduction to stochastic or even deterministic dynamic games. And there are many challenges here. The dynamic game theory has not been fully developed, and at least a theory which applies to all possible settings and scenarios. And particularly if there is asymmetric information, in other words, and which is very natural if you have a very large number of agents, they don't necessarily share all the information, and they may actually use only their local information, locally available information. So this is what I would call asymmetric information. And then this brings us as one way of resolving the challenging issues that arise in this context, the mean field games. Now, to be more specific, I will focus on linear quadratic mean field games, and both within the context of consensus as well as consensus and dissensus. So that will be the new twist into game theoretic formulations. And we'll talk about the existence and uniqueness of the relevant solution concept in this context, which is the mean field equilibrium. And then the question is, this is an asymptotics, you go to the regime of infinite number of players or infinite number of agents or infinite populations. What if the solution that you obtain in that context, if you want to apply it to finite population games, what do you lose? And so that brings us to epsilon Nash equilibria for mean field, a guarantee that mean field equilibria would provide, and then one can obtain sort of a relationship between epsilon and the number of players in this finite population, and this gives you a metric, a measure of what you lose. Now, this is all good if all agents have access, as we'll see shortly, have access to the entire modeling framework, the entire information in the game. Not necessarily the information the agents make, but the underlying system dynamics and so on. Now, what happens if you do not have that? Then, of course, the learning comes in. And I'll talk a little bit about zero-order stochastic optimization, which was also brought up in one of the previous talks, based on reinforcement learning. And then when you talk about zero-order stochastic optimization, there is a finite sample analysis that comes into picture, and we want to know exactly what the relationship between the number of samples that you take and the accuracy of the decision process. And then if I have time, I'll present some numerical results. So as a general introduction to game theory, it's a modeling and computational framework it provides, and it's unavoidable if you have multiple agents and with misaligned objectives. So game theory does indeed provide the right modeling framework and as well as computational framework to capture interactions among multiple interacting agents, players, actors, all used interchangeably. And they could be physical, economic, social, or even biological. And then the dynamic game theory, if you bring in, it provides an even richer framework which captures the evolutions of these interactions among agents over time. And in that context, the information structures play an important role, as opposed to the case of static games where information structures do not play any role. And so the question is who knows what and when, and what sort of memory restrictions the agents have, how deep into the past the agents recall, and we know that even in control theory, stochastic control, there are serious issues if memory is restricted in obtaining a general theory. So difficulty is compounded in the case of games. There might be resource constraints in terms of the communication among the agents, and how much of their decision they can use over how can they allocate the power that they have over the decision horizon. And the trade-offs between short-term and long-term goals, these all play important roles. Now, coming to the third bullet that I have here is, in the game context, there are multiple solution concepts. There is Nash equilibrium, which corresponds to the case of symmetric roles of players. There is Stackelberg equilibrium, where you have a hierarchy in decision-making. There could be multiple hierarchies. And there could be Markov perfect equilibrium, etc. And these are all tailored to the scenarios at hand. And now, if you go to the infinite population of players, which I briefly mentioned, then the interactions among the players take a different meaning, and that leads to mean field games. And the associated solution concept in that case, which is an extension of Nash equilibrium, is the mean field equilibrium. So let me say just a few things on obtaining the Nash equilibrium in dynamic games. If you have the two extreme cases, in other words, when all players have access to perfect state information, then a dynamic programming type of recursive sort of computation can be carried out to obtain the Nash equilibrium. And if you have an open loop information for all players, then you can use the maximum principle to obtain, again, necessary and sufficient conditions for equilibria. But if you have other types of dynamic information structures, such as each player has access only to local state information, or decentralized, or measurement feedback, then these are extremely challenging problems, and possibly, even in the case of linear, quadratic, non-zero-sum stochastic differential games or dynamic games, you possibly have infinite dimensional decision rules or controllers, as we might say. And why is this the case? Because players interact over a horizon in a dynamic game, and through the interaction, they can learn something about the environment which they themselves have not access to, but which may be useful in their decision-making process. So there is the second-guessing phenomenon that comes in. You have to second-guess what information the other players who have acted in the game have access to. Note that this is a dynamic process, so therefore you do have, there's a learning aspect of it along the way. And generally there is, if you have a certain graph topology, you interact with your neighbors, but you may not have all the information that your neighbors have. So each player, each agent tries to second guess what the other one has. But if they do this, then this leads to an infinite recursion. So agent A will try to guess what agent B has that's relevant to the decision-making process of agent A. But then the agent B would like to know what agent A knows about what he knows. And so this is an infinite recursion. And asymptotically, there is a learning relevant information can be retained. Even obtaining approximate Nash equilibrium is a formidable task in this case. You can say, okay, we cannot obtain the Nash equilibrium, let's put some restrictions on the dimensions of the policies, and these are actually NP-hard problems. So the question is this the end of the road? Fortunately not. And mean field games approach is the answer, provided that the game that you have fits into this framework. So what you do is you lift the n-player game up to an appropriate infinite population one, assuming that one exists, which also respects the neighborhood relationships. Now, once you do that, then from each generic agent's point of view, the rest of the system or the decision process of the other agents enters as an aggregate quantity. And the strong law of large numbers generally kicks in, and each agent essentially faces a stochastic control problem. And so this is a problem where an agent responds to the aggregate decisions of other agents, but as I indicated with the strong law of large numbers, that maybe could be pre-computed. And the important thing is that each agent is an infinitesimal decision maker in this process. So therefore, any deviation of that agent's policy or decision does not affect that aggregate quantity. So you solve the stochastic control problem for each agent, and then you generate the state process and other possible aggregate quantities under these optimal control policies. But in solving this stochastic control problem, one had to assume what that aggregate quantity is, which is the aggregate of the decisions of other agents. Okay, that is a parameter into your problem. And then you go, and if each agent acts the same way, then you go for consistency and solve a fixed point equation in order to obtain that aggregate quantity. So the optimal control policies, together with this aggregate quantity computed, which is the solution of a fixed point equation, leads to what we call a mean field equilibrium. And a lot of work has been done in different contexts, looking at the existence, uniqueness, and characterizations of these. And a lot can be said, actually, even for general nonlinear models. And then the next thing to do is, once you have a satisfactory solution for this infinite population game, you study you say, how can I use that solution in a finite population game? And one studies the relationship between finite n, that's the size of the population, and the infinite n solutions, and that leads to an epsilon Nash equilibrium. And thus, this resolves the formidable task of obtaining approximate Nash equilibrium for games with asymmetric information, such as local measurements only, for example. And this is the only way I know of where, if n is sufficiently large, where you can obtain an approximate solution. So now, what are the computational aspects of this? Now, one advantage of the mean field equilibrium-based solution and approximate Nash equilibrium policy is that it's scalable. You can scale it up because it was derived originally for an infinite population game. Now, the computation of the mean field of Nash equilibrium requires solution of a fixed point equation, but that requires full modeling knowledge. But the players may not have access to that. So one way around this is for each agent to interact with a central coordinator or simulator, let's call it, and the simulator collects state values of the agents from different agents and computes the mean field, that aggregate quantity that I mentioned, and broadcasts it to all the agents. So now this is a scheme which also maintains privacy, which so the agents do not have to share their specific models, the models according to which they are making the decisions. So the agents then update their policies based on the received mean field, and then recompute their state and send it to the central coordinator, and so on. The process continues, and then the research issues here are, does this process converge? Now, if you have multiple populations, then let's say you have L different populations, then you have L different mean fields. So therefore, but it has to be a finite number. And the central simulator computes, therefore, L different mean fields instead of a single mean field. Now, the next question is, what if the agents do not know their own models? And then one brings in reinforcement learning for each agent into the iterative learning process. And this is what the latter part of the talk is going to address. As I mentioned, the one way of approaching this is through zero-order stochastic optimization, the ZSO techniques, and we can show that actually multi-agent reinforcement learning in large heterogeneous populations can be effectively addressed within the framework of mean field games. Okay, so let me just say, because I won't be able to cover everything in these papers, but the main reference for this talk, for the rest of this talk, is with consensus and dissensus, is this paper which just appeared a few months ago in Dynamic Games and Applications. And Anik is a PhD student of mine, and Eric was a postdoc. He is now in Ireland with IBM Research. And an earlier sort of work on this also involved Kai-Ching Zhang, who's here, and he's a faculty member at University of Maryland. Okay, so now coming down to the consensus problem, let's see what sort of a model we have and how we can generate the mean field equilibrium, and from there go to the finite population model. So I'm going to stay within the linear quadratic framework because you can accomplish a lot and obtain explicit solutions in that context. So you have a linear for agent n. You have a linear state equation, and W is the noise, Gaussian noise. U is the decision variable, and Z is the state. And the agent has local information only. In other words, so this is a game where you have capital N agents, but each agent has access, has a separate dynamics, and has access only to his own state. And so this is what is called the local state information. Now the coupling between the agents comes through the objective function, and this is the consensus problem. And so you have the regulation, each agent. So if I had only that term, then the problem would be completely decoupled, and there wouldn't be a game. And what makes it a game and one where standard techniques cannot be used because of the local state information, the information is not shared by all, is this consensus term. And essentially what it says is that the agent N wants to pick his control policy in such a way that the state, that agent state, is going to be as close as possible to the average states of all other agents. Okay, so this is the consensus, and it's on an infinite horizon. This is formulated. So the Nash epsilon Nash equilibrium in this context is very well known, and what it is. So you want to come up with a set of policies such that if you fix the policies of all agents except the nth one, the nth agent cannot do any better than an epsilon optimality. And so in this case, the Q and the weighting matrices are just standard sort of non-positive, non-negative definite and positive definite, and we have some the standard controllability and observability conditions also. So what's the mean field approach? As n goes to infinity, then you have note that this was independent, the state equation. The matrices A and B were not player dependent. I will come to the player dependent case shortly. And so the mean field itself, which is the average state of all other agents, is Z bar. And so as I indicated earlier, the nth agent, or each generic agent in this case, is faced with a stochastic control problem. But it's a target tracking problem in a sense. So again, you have the regulation term, and you also have the consensus term. Okay? And so this is a linear quadratic tracking problem, and the local information, Z, that's all you need in this case. Each agent has to access only to his own state, and you can use the standard theory to obtain the solution. Now, but we don't know what Z bar is, but using the law of large numbers, Z bar can be viewed as a deterministic process. So what one does is given Z bar, you solve the stochastic control problem to obtain the policy of that agent. And then you go for consistency, you substitute that policy into the state equation of that agent, and then find the evolution of that average states. And so this pair here that we have is a mean field equilibrium in this case. So it is the policy of the agent and the aggregate quantity. And one can actually show that there exists a unique solution here, mean field equilibrium under the standard assumptions of controllability and observability. And then the mean field equilibrium is also an epsilon Nash. So this closes this chapter, that what happens if you use the policies that you have obtained for the n-agent game, and it turns out that the kind of approximation that you have, how much you lose, or this is in the epsilon Nash equilibria, what the epsilon is, it's in the order of 1 over square root of n. Okay? And so this way one can obtain a solution to the approximate Nash equilibrium without going directly to the n-player game, which is impossible to solve. Okay, so now let's go to the consensus and dissensus problem. We have multi-populations. There are L populations and N sub L agents in each population. Each agent in each population has, again, a linear dynamics. And note that the A has an index superscript L, so which means that it could be different across different populations. And again, the agents have local information only. So you have the regulation term, and you have the intra-population consensus, which means that each agent wants to be as close as possible to the average opinions of other agents within that population. And then there is this interpopulation consensus or dissensus term, where each agent in population N, or L in this case, wants to stay away from the average opinion of other agents in other populations by a positive factor of beta to the LK. And beta LK, where LK is an index, it depends on both the agent himself as well as the populations. Okay, so this is a sort of you want to be as close as possible to to people that you agree with in your own sort of population, and then you want to stay as far as possible, and how far depends on the nature of the populations. So the beta will depend on K itself. So one can introduce an epsilon Nash equilibrium in this case. Again, this is a game where you have n sub L agents, and there are L populations, so the summation of n sub L over L, so that many agents in the game. And so you can introduce the mean field game in this case, but the mean field game will have different aggregate quantities for different populations. So you have L populations, so L different aggregate quantities. So again, you have the regulation term, and you have the interpopulation consensus term, and this is the interpopulation consensus or dissensus term. Again, the beta is a positive quantity here. So note that each agent, again, in each population is facing a stochastic control problem, but there are now three L different aggregate quantities that it's responding to, or that it will be tracking. But it's not tracking the Z bar K, the aggregate quantity of another population, but will be tracking beta plus that dynamics. So again, one can introduce the sort of what is needed here. You solve the optimality is the solution of that stochastic control problem, and also you go for consistency. That is the aggregate quantities that you have taken, the L of them, are consistent with what comes out of the decision-making process. So that again leads to a fixed point theorem. So one has to solve for Z bar star, which is now an L dimensional, or could be higher dimensional if each one is of higher dimension, and so this is the fixed point equation. So now, what is the nature of the solution in this case? The nature of the solution is this is a linear quadratic tracking problem again, and but you have multiple sort of aggregate quantities that you want to track with some distance of beta. So the solution of the stochastic control problem is linear, affine, in the local measurements of that agent, and in the aggregate quantity. This is the vector of aggregate quantities of all agents, and then some constant. And this constant is here because of the beta. And the aggregate quantity, or the mean field itself, evolves according to another linear equation where F star and C star can be computed if you have full knowledge of the underlying dynamics and so on. Now the C star is there because the beta is not equal to 0, because of the beta. So if betas had been equal to 0, then this would be totally linear, and this would also be totally linear. And so these are the linear terms, as I said, so these are the offset terms. So one can prove the existence and uniqueness of mean field equilibrium in this case. Details can be found in that paper. And this is obtained using a probabilistic approach, and the implications of that proposition, which I had on the previous slide, is that at equilibrium, mean field has deterministic affine dynamics, which which leads to an offline computation, and that will be very useful in the learning side. And the controller is causal, and it's distributed and affine. It uses only local information for each agent, and it's definitely also scalable if you use it in the finite agent domain. And this causality of the controller, the causal controller, allows for reinforcement learning in this non-stationary setting. Generally, reinforcement learning in multi-agent or multi-agent reinforcement learning is a very tough problem because of non-stationarity that emerges from the interactions of the players. The environment changes because the other agents, from the perspective of a single agent, other agents decisions are time varying, and they impact the environment that the generic agent sees. And so this overcomes that difficulty. So the question is, what if I use this for a finite population game? In other words, each population is finite. How much do I lose? Is there an epsilon Nash equilibrium in this case? And indeed there is, and this is a very lengthy proof of this result, but the result is very intuitive. For each agent, you look at the neighbors of that agent. There is an underlying topology here, which I have not indicated, which is quite arbitrary. And you look at the neighbors of those agents, neighboring populations. It is governed by the smallest neighboring population, including the population of that agent. Note that in the case of the single population game, what we had was that it was all 1 over square root of n, which was the size of that population. So in this case, it is the size of neighboring populations also come into play, and including the population that particular agent is in, and this is the approximate Nash equilibrium that one obtains. And I'm not, I'll not do anything further on this. So now the next thing is how can we bring in reinforcement learning for these multi-population mean field games? Again, as I indicated, reinforcement learning algorithms for linear quadratic mean field games in the literature deal with stationary equilibria. Here we do not have stationary equilibria. And they deal only with the single population setting, and they are not truly model-free. So here we are looking for model-free, but within the linear quadratic framework. That is, these matrices, the A, L, and BL, they are not known, as well as the cost parameters. And so each agent is unaware of his dynamics and cost function, and has access to only noisy estimate of the controller cost. And one can use also zero-order stochastic optimization-based RL. Now, the way to approach this, the reinforcement learning is by reformulating the problem as drifted LQR. And note that you have the state from each agent's point of view. There is the state of that agent Z. There is also the aggregate, the mean field itself, but this involves L populations. So let's call this vector XL, and then it evolves according to a linear equation. And then, so what we don't know are these F's. F was what came out of the fixed point equation. We don't know what F is, we don't know what C is, so these are to be learned, and we don't know what AL and BL are. And you can formulate the cost of agent L for this reinforcement learning purpose in this form. And so therefore the X is trying to get close to beta bar L, and then you want to do it under some constraint on the control. So this is equivalent to what I had formulated earlier, but this is for drifted LQR for reinforcement learning purpose. Now the thing is that you can actually decompose that cost into two parts and plus some total constant, and the important thing here is that if you let the offset terms to be equal to 0, then you just have the first term, so you can learn as though you don't have these offset terms. You learn the k, in this case gain, and then you come back and then you learn the KL2, and then as well as the other parameters. And so this reinforcement learning algorithm is divided into two parts for each agent. The first part estimates the linear terms, and the second part estimates the offset terms. And in both parts, we use actually Each agent will use the zero-order stochastic optimization to estimate the controller parameters. And the central simulator computes the mean field under this set of controllers, and which is a multidimensional vector. And then this process continues, and we can prove that the process actually converges. I'll not go into the details. So this is what the central processor does, and this is the aggregate quantity, and we have the linear mean field in the first part of the algorithm, and in the second part of the algorithm, the C kicks in. So you can learn F and C independently, in a sense. So I'm running out of time, and so we have several algorithms actually, which you can find in the paper, where you estimate the linear terms. You use the zero-order stochastic optimization for the linear controller, and then the simulator updates the linear mean field, and then you do you continue this process. And then you come back and estimate the offset terms separately after you do the gains without the offset terms. And then you again do ZSO updates for the control, and then the simulation updates. Okay, so the zero, I think this community knows what ZSO algorithm does. So I'm going to and then we have the finite sample guarantees, and fairly complicated expressions, but at least I mean the good news is that you can obtain explicit sort of bounds on the convergence of these algorithms. Okay, so I'll conclude actually. I don't have time, so I have to go into the numerical studies. So I addressed the multi-agent reinforcement learning from a mean field gain perspective. We have heterogeneous agents grouped in populations, and I discussed the existence, uniqueness, and affine structure of the mean field equilibrium, and also the epsilon Nash guarantees. And it's the affine structure that has inspired this two-part RL algorithm, and if we have a nonlinear system dynamics, that will be a challenge. And ZSO techniques were used in the RL algorithm. And then we have finite sample convergence guarantees. So my final slide is sort of what lies ahead in this, for this class of problems. One thing is I haven't addressed robustness. So one way of introducing robustness is through risk sensitivity. And this is perfect local state measurements. What happens? You have imperfect local state measurements for the agents. And the other thing I have assumed throughout this analysis, that the populations are fixed in advance. In other words, there is no sort of migration from one population to another, and which makes sense in the current climate of the political climate of United States, but it's something if you want to address other types of scenarios that may be necessary to allow for some migration. And the other thing is, what if agents do not obey the rules of the algorithm? All this is assuming that each agent is a perfect optimizer. And what if there is irrational behavior and stubbornness? How many agents can you, in an infinite population, if there's only a finite number of agents who are stubborn, then that does not make any dent into the analysis. But if you have a finite population, then it does. And then the hierarchical decision structures, and how can we incentivize agents toward the truthful revelation and also more general nonlinear models. Thank you.
Thank you for a very inspiring talk. We have time for a few questions.
Thanks for the great talk. Amazing results. Can you comment on the applicability of these results? So what do you have in mind? You seem to think about social networks or opinion dynamics, but then what would be the matrices A and the input U? Or is it decentralized computations? I'm not sure I see what you have in mind.
Well, as I indicated, the consensus, dissensus is definitely has relevance to social sciences and political sciences. So that's one main application area. But also we know that consensus problems have been used to look into flocking, for example. And then you want to maintain a certain distance between different groups of aircraft and so on. And some have to be closer to each other, some will have to maintain a certain distance. And this, of course, theory will apply to that context as well.
Thanks.
Hi, I had a question that in the setting when you have heterogeneous populations, does each agent know which system should go into the consensus part and which system should go into the dissensus part? Or is it something like over time each agent does some sort of a clustering to realize, these systems are close to me, these are far away, and accordingly adjust the objective function?
Well, the consensus part is not heterogeneous. You have heterogeneity across different populations. So I assume that different populations are fixed, so there's no migration. And so therefore the agents know when they interact with others, they hear their opinions and they say, no, I want to stay away from that by an amount beta. And so with some other populations, if they are way out of the spectrum, the opinions, the beta will be higher. And so therefore, when they interact with different agents, they can, in other populations, they can tell what population they belong to.
I see. But when the opinions get transferred, I guess there's noise in it. And so that would, you wouldn't probably have an immediate estimate of who's close and who's far. And probably there's some stochastic process there as well that informs you over time what the beta should be and who's close and who's far away. Or is that something that happens immediately?
I think you can definitely evolve in that direction also, and learning which agents belong to which populations and so on. But the noise here in identifying membership in a population, noise does not play any role that much.
I see.
I'm assuming that there is enough separation that even if it is you do observe the average of the opinion of some group of agents. So therefore, that average is not, when you take the average and there's a large number of them, the noise does not play any role there.
Thank you so much.
Let's thank Professor Bashar again for his talk. And we'll move on to the next session.
All right, welcome everyone to the final contributed session. Our first talk is Lipschitz constant estimation for 1D convolutional neural networks, and I have Patricia Pauly presenting.
Thank you.
Thank you, and welcome to my presentation on Lipschitz constant estimation for 1D convolutional neural networks. This is joint work with Dennis Gramlich and my PhD advisor, Frank Algöver. So convolutional neural networks played a big role in the success of deep learning, and they're applied in so many fields, in image processing and video processing, like in classification trusts of pictures. Also, 1D convolutional neural networks appear in the classification of medical data, or also in segmentation tasks. We see neural networks. However, there are still some problems with neural networks, and one of these is that they may be susceptible to adversarial attacks. What that means is something you can see in this example. Here we have a picture of people in the street, and a neural network was trained to identify them. Now, adversarial noise is added such that the picture is hardly changed. It looks very much the same, but the segmentation is completely different, and we cannot see the people in the street anymore. This is, of course, very dangerous in safety-critical applications and not desirable. But what can we do? As control engineers, control engineers have expertise in giving guarantees. We have a well-established field with all these mathematical tools, and we want to use now this knowledge and apply it to analyze the robustness of convolutional neural networks. If we now talk about robustness, what do we mean? So we use the Lipschitz constant as a robustness measure. In this box, you see what Lipschitz continuity is. If this inequality holds for some function, then it's Lipschitz continuous. And if we have a small change in the input between x and y, and also a low Lipschitz constant, then we have a bound on the change in the output. And that's what we want. So a low Lipschitz constant means high robustness in the notion of robustness we want to use throughout this talk. And what are we doing now? Sorry. Now it's frozen. Now it's working again. There we go. We want to provide a scalable, semi-definite programming-based method for Lipschitz constant estimation for 1D convolutional neural networks, and therein we also exploit the specific structure we have in convolutions. And now, well, we've talked about that we want to know the Lipschitz constant of the input-output mapping of a convolutional neural network, and so this problem is NP hard, and for deep neural networks, it's really not feasible to find the exact Lipschitz constant. What can we do instead? We can over-approximate the nonlinearities, and we can determine upper bounds on the Lipschitz constant. And to be more specific, what we want to exploit in this over-approximation is that the activation functions that are commonly used, for example, tanh and ReLU that you can see in this figure, they are slope restricted. That means their slope for all inputs is between 0 and 1 for these two examples. And this property can be captured by an incremental quadratic constraint that you see in this lemma here. And it really incorporates all the neurons, the overall neural network, and their lambda here is a multiplier that will later on appear as a multiplier that gives us degrees of freedom in the analysis. Where does this idea come from? It comes from here. It comes from Japan, and so there was a paper in 2019 that used slope restriction for activation functions in the context of neural networks, and which is this paper. They developed a method called libSDP, which is a semi-definite program to find an upper bound on Lipschitz constant of a feed-forward, fully connected neural network. So this approach is also applicable to convolutional neural networks that we are looking at today. But it has limited scalability. And why is that? Well, it requires the formulation of convolutions as fully connected layers with a tuplets matrix, which is very sparse and highly redundant. And also, the authors from this paper proposed a large and sparse linear matrix inequality condition. We will tackle both these points for the case of convolutional neural networks, have a more scalable semi-definite program in the end. And let's look at convolutional neural networks. 1D convolutional neural networks is what we're focusing on today for ease of exposition. The approach really also applies to 2D convolutional neural networks that are definitely more popular. But let's stick to the 1D CNNs for now. We have some signal as an input. We have several convolutional layers followed by nonlinear activation functions. We might have some pooling layers. At some point, the output is flattened, and we add some linear, fully connected layers in the end of the neural network. And what we claim now is that every single individual layer that we have in the setup is QSR dissipative, meaning that it satisfies this property. And that means that the convolutional layers, the pooling layers, and also the fully connected layers, all of them, looked at them separately, are dissipative. And if we have these properties for the individual layers, we can connect the input to the output of the neural network through these dissipativity properties, and that will help us to find something out about the input-output property Lipschitz continuity of the whole convolutional neural network. Let's look at the layers that give the convolutional neural network its name. So we can state convolutions and convolutional layers in this way. They're characterized by some bias term and by some kernel K, some filter K. But we want a different formulation, and what we point out is that this is an FIR filter, and this is a dynamical system, and we can find a discrete time state space representation as such for this convolutional layer instead, which is a nice description which will help us in the analysis. This is just an example. A and B have some structure, and C and D hold the parameters from the kernel. And with that, now we can formulate a linear matrix inequality, which is a sufficient condition for QSR dissipativity for the convolutional layer. It doesn't really matter what it looks like, but it has A, B, C, and D in there, which are coming from the given convolutional layer, and some multipliers, and this now gives us QSR dissipativity. We can also formulate a very similar LMI condition for fully connected layers that will also give us QSR dissipativity for those layers. And with that, let's go to pooling layers. Pooling layers are used for downsampling, and there are possibly nonlinear operations. And what we did here was that we formulated an incremental quadratic constraint coming from the structure and the properties of the pooling layer itself that looks like that. And if you now look at this matrix, you can see that this is really an instance of QSR dissipativity as it is, where you choose Q, S, and R as given on the bottom of this lemma. We can do a very similar thing when it comes to maximum pooling layers and also formulate an incremental quadratic constraint. So these two are they're definitely QSR dissipative. And so are all the layers. They are QSR dissipative. We just have to find the QS and R, and I claim there is one. And now with this property, now we have to account for the interconnection structure, which is really just feed forward, and we can do that using this coupling matrix. And with that, we're coming to the main result. If we have a given convolutional neural network, and now if there exists some QSR such that the dissipativity LMIs that we've seen are satisfied for the fully connected and the convolutional layers, and also the coupling LMI holds, then the convolutional neural network is gamma Lipschitz continuous. And how do we now use this to find an upper bound on the Lipschitz constant that is possibly quite tight? Well, what we do is we solve a semi-definite program that we can see here. It has a bunch of decision variables, QSR being among them, and we minimize gamma squared. Gamma corresponds to our Lipschitz bond subject to all the LMIs that we've already seen and discussed. Now that we've seen this method, let's look at simulation for a little bit. And here in this first example, we looked at a fully convolutional neural network. That means we just have convolutional layers, no linear layers, no pooling layers, just the convolutional layers. And we compare our method to libSDP from the paper that we've talked about before, and to the spectral norm bound, which is a very loose bound coming from the product of the spectral norms of the weights. And if we compare the methods, we can see that our method compares very well to libSDP when it comes to the Lipschitz bound, but now looking at the computation time, we see the advantage of our method. The computation time is really independent of the input dimension. We're increasing the input dimension on the x-axis here. And this is a logarithmic plot, so this is really a nice property and shows improved scalability. Now we applied the method as well to the structure we've looked at before of deep convolutional neural networks. And here you can see in the little picture what the convolutional neural network that we're looking at looks like. We varied the channel sizes C1 and C2, and now use libSDP again, compared it to our method and to the spectral norm bound method. We can see here that our method always has a tighter bound than the spectral norm bound method. Is here a little bit worse than libSDP, but the advantage becomes apparent again when we look at the computation time, where the bar of our method hardly appears at all in this picture. And we can see that our method scales better. And with that, I'm at the end of this presentation. We've seen a scalable SDP-based Lipschitz constant estimation for 1D convolutional neural networks. We saw a distributivity-based approach which helped us with scalability also, which is new, that we had a compact state space representation of the convolutional layers, which is much more favorable than the triplets matrices, and we formulated incremental quadratic constraints for possibly nonlinear pooling layers. Also, let's give you a short outlook. We've kept working on this topic, and we've by now extended the work to 2D convolutional neural networks using a 2D system state space representation. This work is on arXiv, and also we've looked into training of Lipschitz-bounded 1D convolutional neural networks, which you can also find on arXiv. So thank you very much for your attention.
All right, we have maybe time for a question or two. And meanwhile, I'd like to ask the next speaker to come up and get ready.
Thanks for your talk. Very interesting product. Actually, I look at your outlook, and that's just two of my questions that I just want to ask you. Like, what's your initial thought of extending it to 2D CNN, and how can you use it as a regularization term? And you just answered it in the outlook, so I have an additional question. So in some of the neural network training, we need to do some extra operations. For example, for depth estimation, normally people will use 1/d rather than d when they're estimating the depths. So I wonder, like, is there a way to quantify what kind of operations that you can use building upon the 1D CNN that you already have? Yeah, so my question is mainly about the Lipschitz estimation for some extra operations other than the 1D CNN in the network learning. Yeah.
Give her a mic.
Okay, so basically it's like you can add an additional layer on top of that and do the further analysis. Is that, am I understanding it correctly?
You could, yeah, you can really, if you wanted to, you can add additional layers, and there could also be different, even different layers that we haven't even looked into in this work, as long as they have the property that we need of being dissipative.
Okay, thank you.
Yeah, so very interesting talk. Thank you so here. Hello, can you? Right here on the right corner.
I think we have to go on to the next talk, sorry.
Oh, okay, no problem.
Are you ready? All right, so the next talk will be by Karthik Alamvasvuti. Whenever you're ready. Yeah.
All right, thank you. Never been so higher in sea level than the rest of the crowd. I finally feel like a scholar as it sits there, a postdoctoral scholar. Yeah, from University of California, Riverside. And so I'm going to be continuing on the theme of using control theory to understand neural networks. What kind of insights can we use from, like, so far 30 years of, I mean, how much is it? 50, 100, whatever. Number of years of insights in control theory to gain some insights on neural networks. So I'm going to be talking about a specific kind of neural network, which is almost the norm these days of using ResNets, right? Residual neural networks, where so you can look at a neural network as a discrete dynamical system. Right? And in a residual neural network, you have these feed-forward connections from one layer to a subsequent layer. So you can look at this as an iterative dynamical system, and the machine learning or approximation problem can be thought of as a control problem for this discrete dynamical system, where you have these weight parameters, an, wn, and theta n. And you have this given activation function, and you want to achieve some desired behavior for this discrete dynamical system. And the point of view, and the general approximation question that is of interest in this situation is that you're given a map, and given a map, say it comes from data, how well can you use the output of this neural network, of this ResNet, or this dynamical system, to approximate arbitrarily well this given map F. And more specifically, the question that we are interested in and where we want to shed use tools from control theory to shed light is what is the role of depth. So in recent years, one of the big things about neural networks is that somehow making them extremely deep has revolutionized how neural networks, their capabilities of how well they function, right? So what is the role of depth? And what does this mean in the control theoretic perspective? So in order to use control theory, so what we do is take a continuous time approximation. I mean, this is not something we do specifically, and this has been done in the past. You can look at this discrete dynamical system as a forward Euler approximation of a related continuous time ordinary differential equation known as the neural ODE. And that's the second equation here in the slide. And yeah, and then you can, so what happens is that in some sense you're taking an infinite number of, you're considering the limit where you have an infinite number of layers. And the time variable now is a continuous parameter which parameterizes how deep you are in the layer. And now we can pose the same problem of approximation using this neural ODE. Given a map, you have these parameters which are now time dependent. How close can you make your given map? How close can you make the flow map of your neural ODE as close as possible to this map that comes from data, right? And this is a sort of non-traditional control problem. If you look at this approximation problem in terms of control, because you're not just trying to map one single point to another. What you're trying to do is simultaneously take a number of input data and map it to the output data, right? So in some sense, you can think of this as a multi-agent control problem. You're simultaneously trying to use the flow of the dynamical system to map it from one configuration to the other. So it's in some sense an infinite dimensional control problem, right? Because you have an infinite number of points that need to be mapped simultaneously. And this problem of approximation was recently addressed by Tabuada and Gerasimov in this recent paper, where they identified some geometric criteria and showed that for a large class of activation functions, using the depth alone, that is by keeping the width bounded by the dimension of the input data, you can make the neural ODE approximate a given map arbitrarily well. In practice, many of the examples that we consider in literature, for example, in robotics, a lot of the systems that you saw, we have some additional information about the data, right? For example, we know that the data is constrained to a manifold. This could be yeah, as I said, in mechanical systems, you often have these rotational degrees of freedoms. So the natural state space of the system is some nonlinear manifold. So we modify a neural ODE to account for this information. So how do you encode this information into a neural ODE? Because as such, a neural ODE does not keep a given set or a manifold invariant, yeah, without further modifications. So we introduce a class of neural ODE which takes this information into account, where we introduce these vector fields which ensure that your data remains on the manifold by defining it in such a way that it takes values only on the tangent space of the manifold. And by construction, this new neural ODE keeps the manifold invariant. And we can ask the same question. Given this situation, does this neural ODE have, can it approximate an arbitrary map that keeps a manifold invariant? Can we make it epsilon close uniformly on the manifold? So the result that we have is the following. So so given that the map that you want to approximate has this property, that is, it's isotopic to the identity, which just means that it can be smoothly mapped from the identity map, then the flow of your this geometric neural ODE can approximate your this given given map arbitrarily well by choosing suitable piecewise constant weight parameters, or in this instance, we are thinking of them as controls. And to give you an example of what it means to be isotopic to an identity, if you know that your given map itself is coming from the flow of another dynamical system, now that's a good example of a map that is isotopic to the identity. So if you have just some arbitrary dynamical system that's staying on the manifold, say it's a robot, right, like a multi-arm robot, so that would define a map that is isotopic to the identity. And the sufficient condition for when we have a good representation is the following. It's that this controllability on the set of maps, of flow maps, turns out to be related to a much simpler controllability problem. That is controllability of this related control system, which all of us are familiar with, a control-affine system. So it turns out that if this system is controllable from a single point to an arbitrary point on the manifold, then this neural ODE that we have constructed is controllable on the set of maps, right? So all we need to know is that these vector fields Gi that we have picked to stay on the tangent space of the manifold satisfies the nonlinear analog of Kalman rank condition. Right? We can use like these Lie brackets between these vector fields to test whether your neural ODE is well defined from a representation point of view. And also another key thing is that this works for all the activation functions that you would think of in practice, right? So that's another sufficient condition. Any activation function that you would think of, and suppose your GIs are rich enough, they satisfy this rank condition, your neural ODE, geometric neural ODE, has good representation. And we applied this example on a sphere where we use these two vector fields defined by these skew-symmetric matrices. And if you compute the brackets between these two vector fields, you can recover, you get all the directions everywhere on the sphere. So this is a well-posed geometric neural ODE. And then when you implement it, of course, you need a discretization, but you don't take a usual forward Euler discretization of this neural ODE. You use a geometric discretization. And then you can plug it into your solver, such as PyTorch, do automatic differentiation, and fit data to this model. And so we applied this on a toy example where the map is generated by this dynamical system. And one thing I want to emphasize is that the right-hand side in this dynamical system cannot be approximated by the vector field of the neural ODE. But it's truly a control theoretic feature of the system is that you're able to not approximate at the vector field level, but you're still able to approximate the map itself, right? Because of these bracket generating property. And then we also compared it with classical neural ODE, which does not take into account this manifold information. And we saw that the manifold invariant one performs better. And we also applied this on SO3 on an example on the set of rotational matrices. And we observed the same kind of behavior. And this has other applications as well. For example, you could also use this because feedback control of a control-affine system is also the problem of mapping a number of, if you want to stabilize, it's the same as mapping a family of points to a single point, right, using the flow map. So you could use this for feedback control using a neural network. And of course, instead of calling it input and output data, you could also call it an agent or a robot. And you can do multi-robot control using this kind of a neural ODE. And you might ask, why would I want to use this? So for the same reason, people prefer deep neural networks. So maybe these kind of geometric neural ODEs are much more scalable when it comes to doing multi-robot or multi-agent control. So I think it has several applications, and it opens up a large number of problems in control theory when it comes to analyzing these kind of systems. All right, thank you. So if you have any questions, I'll be happy to take them.
Question or two? We have time for a question or two.
So much. Do you need to have any constraints on the weight matrices of the neural network so that the network is invariant, the neural ODE is invariant?
No, you don't need to impose any conditions on the weights themselves for the invariance. That just naturally comes from the choice of G. But you might need to, you might want to regularize it for different reasons, right? Say you want some sort of robustness or something.
Thank you.
Hi, nice presentation. So just a question. Oh.
Here, please.
Maybe do you have any thoughts about whether this, you're using this, on building the structure, let's say, of this neural network, right?
Mm-hmm.
Anything that has to do with the training process of such a neural network? Do you think there's a, your results can have an impact on the training itself?
On the training, how to do the training?
Yeah.
So we haven't. The way we did the training was just geometrically discretize it and just applied it in a sort of black box way, like use PyTorch to compute, to do the backward propagation, right? So does that answer your question? So
Yes, partly in the sense that, you know, I understand that you didn't exploit the particular way that you used to build it to, you know, influence the training process. But I was just wondering whether there is a connection, perhaps, that, you know.
I mean, there are also other ways of training. So, for example, you could just use an optimal control approach directly without discretizing. You could like sort of do frame the optimality conditions at the continuum level and then like solve it, right? So it opens like a lot of questions as to how you would train in different ways.
Thanks.
Thank you. All right, it's time for our next speaker, Songzhuang Zhang. Please take it away.
Thank you very much. Hello, everyone. I'm Songyuan from the Reliable Autonomous Systems Lab at MIT. Today, I'm going to talk about how to learn a decentralized stabilizing controllers for network dynamical systems. My advisor is Professor Zhu Fan, and I also collaborate with Yu Meng and Professor Chu from CMU. So large-scale network dynamical system plays an important role and with a wide spectrum of real-world applications. And control in particularly stabilizing such system has long been recognized as a challenging problem. So here are three kinds of typical dynamical systems. The first, drone swarm, where we want the drones to be controlled that they can fly in a formation and finish some tasks. And second one, power grid, where we want to stabilize the voltage and frequency of the network metal grids. And truck platoon, where we want the trucks to drive in a predefined formation. Network dynamical systems are often constructed by many small subsystems, and these small subsystems interconnected with each other to form the large network dynamical system. As a consequence, the dynamics of each subsystem are not isolated, but they can be influenced by their neighbors. So such systems are often hard to be controlled because first, the state space of the whole system can be very large that it's very hard to design a centralized controller to control it. And second, even if we can use decentralized controllers, the number of subsystems can still be very large that we don't want to design a specific controller for each subsystem. And third, the dynamics can have uncertainties, which we say the robustness problem. So thinking of stabilizing a system, the first thing that comes to our mind may be the Lyapunov functions. So simply put, if we take the whole system, the states as x, and if we can find the function that is 0 at the draw point, is greater than 0 otherwise, and its time derivative is smaller than 0, then we can say that the whole system is asymptotically stable at the draw. However, as I said before, for such a large network dynamical systems, it's very hard to find a global Lyapunov function. So are there any other ways to stabilize this system? Maybe better in a decentralized way? The answer is yes. The problem of network dynamical system lies in the interconnected dynamics. So for example, if the states of one subsystem grows, it actually can affect its neighbors and the neighbors of neighbors. And finally, back to itself. This can cause a vicious cycle that can finally make the whole system explode. But if we think in the opposite way, what if after this loop, the system actually gets closer to the goal? Then the system is stable. This thought is similar to the small gain theorem. And based on this thought, ISS Lyapunov functions are proposed. So ISS Lyapunov functions are introduced by Professor Jiang from NYU. And instead of being functions of the global states, ISS Lyapunov functions are functions on states of subsystems xi. Its conditions are very similar to the Lyapunov functions. They should be 0 at the goal point. They should be greater than 0 otherwise. But the third condition is a little bit different than the Lyapunov functions. Instead of requiring the time derivative to be negative everywhere, we only need it to be negative when this subsystem is relatively further from the goal than other subsystems. So ISS Lyapunov functions have been introduced for decades. Can it solve the three problems of network dynamical systems? Scalability? Yes. Because now we can just find the ISS Lyapunov functions for each subsystem instead of the global system. So network generalizability? No. Because we still need to find the ISS Lyapunov function and controller for a specific subsystem. And robustness? No, because ISS level functions don't consider system uncertainties. And actually, ISS level functions can bring in a new problem. That is, how can we find such ISS level functions? So here we introduce our approach called neural ISS level functions, in short, NeurISS, to learn ISS level functions for network dynamical systems. So I'll first present some new results based on the original statement of ISS level functions. Let's recall the three conditions of the ISS level functions. The first two are certainly decentralized, but the third one here, the match is taken over all the subsystems, which means we have to compare the optimum value of this subsystem to all the subsystems. So this is somehow a global condition. And we show in our paper that actually this match only needs to be taken among the neighbors. So now these conditions are actually limited to the neighborhood, and it's fully decentralized. So do we need to find ISS level functions for each subsystem? Actually, we prove in our paper that actually if the subsystems have some similarity on structures like symmetry, they can share one ISS level function and one controller. So for example, here, these three can share one ISS level function and one controller, and these three can share another one. And for the robustness, we prove in our paper that if the dynamics are control affine, and if the uncertainties lies inside the convex hull, and if dynamics are affine to the uncertainties, then if we find the ISS level function that satisfies the conditions on the vertices of this convex hull, it's also satisfied inside this convex hull, which is our ISS level function is robust to the uncertainties inside this convex hull. So now we discuss about the final question, that is, how can we learn such ISS level functions? So first, we parameterize the ISS level functions and the controllers using neural networks. So let's recall that we have the network generalizability result. So here, we only need 2 networks for ISS level functions and 2 for the controllers. So now let's design the loss functions. Let's recall the 3 conditions of ISS level functions. The first 2 are very easy to design losses for them, or they can actually simply be satisfied by the construction of the neural networks. But for the third condition, it's a little bit tricky because here is an implied condition here. How do we encode such condition in a neural network training? So this condition actually can be written as A implies B, which is equivalent to negative A or B, which is also equivalent to match of negative A and B. So we directly design the loss function that is of this form, which will punish the violation of negative A and B. In this way, we actually encode the implied condition in the training, and now we can learn the ISS level function and the controller jointly. We conducted experiments in 4 environments, including microgrids, power grids, tracked platoon, and drone swarm. So due to the time limitation, here we only introduce the results of the drone swarm. So in this environment, starting from some random initial positions, we want to control the drones to fly on the grids of a rectangle and to keep the distance between each drone to be the same. And we assume that the drone only has the local observation of the positions of their neighbors, and they are supposed to track an unknown velocity profile. So let's recall the 3 problems of network dynamical system: scalability, network generalizability, and robustness. To test the scalability, we train our algorithm on 4 drone environment and test it on a 100 drone environment. And for network generalizability, we let all the drones share one ISS level function and one controller. And to test the robustness, we model the unknown speed profile that the drones are supposed to track as the uncertainty. We compare with our algorithm with both centralized and decentralized approaches. For centralized approaches, we compare with the RL approach PPO, the RL with Lyapunov created word LY PPO, and the neural centralized control Lyapunov function word NCLF. And for the decentralized approach, we compare our approach with MA PPO, the multi-agent PPO, and the decentralized L2R. So first, we test our approach on a 4 drone environment. We can see that the drone actually forms a groove formation, and the tracking error here is low. For the centralized approach, NCLF, it also forms a good formation, but the tracking error is larger than our algorithm. It's because for the 4-zone environment, the space is still so large for a centralized control left node function. And for the reinforcement learning algorithms, PPO cannot stabilize the system, and LY PPO actually fails on this system. It's because it's hard to provide stability guarantee of RL algorithms, and LY PPO actually learns a centralized left node function along with the reinforcement learning algorithm. So it's already very hard to learn a centralized CLF here. So if we combine it with RL, it will actually lead to worse behavior. And for the decentralized approaches, MA PPO, its behavior is all similar to the PPO, and L2R actually forms a good formation, but still the tracking error is higher than ours. It's because the L2R is for linearized system, and this is a highly nonlinear system. And we directly test our approach along the 100 zone environment. We can see that zone forms a good formation, and the tracking error is low. Although actually the distance is a little bit, there's still some distance difference between each zones because the errors can still accumulate because the zones have only local observations. So here for MA PPO and L2R, the MA PPO actually has a very large error because the errors of 4 zones can accumulate to 100 zones. And L2R actually forms a good formation, but the tracking error is higher because of the nonlinear depth. So although our algorithm solves the scalability, network generalizability, and the robustness of network dynamical systems, we still have the following limitations. The first is we require the knowledge of dynamics. And second, network generalizability results requires the structural similarity of the subsystems. And third, the robustness result needs the disturbance of fine dynamics and the disturbance to be convex. And fourth, it's very computationally efficient. It's very computationally expensive to learn the ISS level functions because neural network verification is an NP-hard problem, so we didn't do it in our paper. So finally, here are our contributions, and you can scan the QR code to reach our project website. Thank you.
We again have time for a question or two, and meanwhile, I'd like the next speaker to come up here, please.
Okay, nice talk, Song Yuan. So I have a question. I noticed this work involves scalability, network generalizability, and robustness. But in some cases, safety is also a very important topic that we need to consider in multi-agent planning. So do you have any thoughts that how can we put safety into this kind of consideration when considering formation control?
Yeah, that's a very good question. Yes, indeed, safety is another very important thing for network dynamical systems. And we actually can bring in the control barrier functions, and it's already part of the future world for this network dynamical system. So we can both learn a ISS level function along with some control barrier functions. So these two functions can act as two different certificates for stability and safety. Thank you.
So nice talk, thank you. You're pointing out that the performance of LQR is worse because it's a linear controller, but it seems like a bit of a strawman baseline. Did you try with iterative LQR to handle the nonlinearity?
No, I haven't tried it before. Try here. Here we want to show that actually the LQR is computed in this way. So first, there is an unknown speed profile, so we want to track. And we design, we say calculate the position of that desired speed profile in each iteration. And then we use that tracking points as the input of L2R. So in this way, we can say L2R is tracking a moving point. So yeah, we will definitely try L2R in this way. Yeah, thank you.
All right, let's introduce our final speaker, and I think our final speaker of the conference even, Fernando Castañeda. Please, take it away.
Yep, thank you. Thank you everyone for sticking around till the final presentation.
So I'm very excited to present this paper. It's titled In Distribution Barrier Functions, Self-Supervised Policy Filters that Avoid Out-of-Distribution States. It's joint work with Haruki Nishimura, Rowan McAllister, Adrian Gaidon from Toyota Research Institute, and my advisor at Berkeley, Kaushal Srinath. And I'm Fernando Castañeda. So the problem that we try to tackle in this paper is distribution shift in control systems when designing learning-based control policies. So if we take this very simple example of having a robot navigating in a road that looks like this, and we have a bunch of demonstrations that we have collected of the robot successfully navigating inside of the road and never leaving the road limits, then we might train a policy, a learning-based policy based on that data using behavioral cloning or offline reinforcement learning and deploying on the real system. The thing is that many times when we deploy this policy, actually the system does something weird. So you get to the limit of the road, get far from the training data, and once you're far from the training data, these learning-based policies might do something completely unexpected that might even take the system farther out. So distribution shift is something that in general we definitely want to avoid when dealing with learning-based policies. So what we want to do in this paper is actually build a framework that in general, when deploying the learning-based policy, doesn't do anything until distribution shift is imminent, so until the robot is about to leave the road. And when the robot is about to leave the road, here, I don't know, yeah. When the robot is about to leave the road there, it rewrites the actions that are trying to bring the robot outside. So the way that we're going to do this is through control barrier functions, which Professor Aaron Ames introduced yesterday very well. And even though the framework that I present here is pure learning-based and it's trained completely end-to-end, we're still going to draw inspiration from control theoretic CBFs to try to enforce long-term constraint satisfaction and control invariance in these learning-based policies. So just a brief introduction to CBFs. So we say that a continuously differentiable function B is a CBF for a safe set X safe if the function is non-negative inside of the set, negative outside, and there exists a control input that always is able to satisfy this condition, which makes the set control invariant. So basically, if there exists a control input satisfying this condition, then the system can remain inside the set. And what that condition says is that as you get close to the boundary of the system, the CBF shouldn't decrease too quickly. And when you get to the actual boundary of the system, the CBF should be non-negative to make sure that you always stay inside. So as Professor Ames talked about yesterday, the typical way to use CBS for control design is as a filter. So given a reference policy that might not be thinking about safety, this might be designed just based on some performance objectives, you find at each time step the closest control input to the reference control input given by the reference policy, subject to the CBF constraint. And this way you make sure that you find control inputs close to the reference, but that keep your system safe. The good thing is that this B dot, if your system is control-affine, and CBF theory is all based on control-affine systems, then this condition is linear in U. So we have a linear constraint and a quadratic objective. So basically we have a quadratic program which can be solved very fast. This is very important because this is a one-time step. It's not taking a horizon, this problem, so it's solved at every time step, and it needs to be solved at the real-time control frequency. But this looks very, very appealing because given a performance control law, you don't need to think about safety when designing this control law, and then you wrap safety around it by using this filter. However, there are some assumptions in here, like that you know the dynamics of your system, F and G, that you have perfect state estimation based on X, and also, probably very importantly, that you know a CBF for your system, that you know the function B. In our setting, we only assume that we actually have safe demonstrations of our system, and that these demonstrations are high-dimensional sensory observations. We don't assume state knowledge. So we don't have any of these assumptions. So what can we do about it? So the approach that we present in this paper, the framework, the learning framework has this form. in which we have a plan that can be an autonomous car, it can be a robot, that gives these high-dimensional sensory observations that might be images, RGB images, or they can be whatever. And based on an encoder, we take those observations and get a latent state, XK. So this encoder is recursive in the sense that it takes the current observation, the previous state, and the previous action, and it gives you the current latent state. Then we train a dynamics model, F and G, and we train a CBF-like function that we call IDBFs in distribution barrier functions, B. And based on the state, the dynamics, and the B function, we can actually now solve the filtering problem for a given reference control policy. So let's dive a little bit in the details of this particular model, the IDBF model, and how it's trained. The idea is very simple. Since we want that function to be close to a CBF and satisfy properties of a CBF, then we're going to enforce in a loss function the three conditions that appear in a CBF loss. This is done by previous approaches. Chang et al., Dawson et al. Did something very similar. And for the particular case of staying in distribution, which is our setup, basically we want the function to be positive, close to the safe demonstration data, negative everywhere else, and satisfy the CBF condition for the demonstrations given, because we know that the demonstrations are safe. However, there's a difference with respect to these previous approaches, which is that in this setup, since what we want is to remain close to the safe demonstrations, and we only have safe demonstrations, how can we actually enforce this second term of the loss, that it has to be negative everywhere else, if we don't have unsafe demonstrations? So for this, we actually take inspiration from noise contrastive learning of energy-based models. And I'm just going to briefly explain what we did, but you can come to the poster session after this and ask me some more questions. But basically, the whole idea is that we first train a behavioral cloning model of the safe demonstrations, and we use this model to select actions that were unlikely taken by the experts. So we take the low likelihood actions based on this behavioral cloning model, and we actually propagate them one time step to generate these unsafe samples. And this creates a contrastive data distribution on which we can encourage the CBF function to be negative and be positive at the training data. Yeah, I'm happy to give more explanation on this at the poster, but yeah. So now, the only thing here is that we're still assuming that we have a state and actually that we have the dynamics of the system in order to compute this B dot. But if we only have the high dimensional observations, what do we do about it? So since the filter based on CBFs is solved very quickly if the system is control-affine, because then it's a quadratic problem, then we're forced to learn a control-affine dynamics model using neural ODEs in a latent state space, actually. And we use the recursive autoencoder that I explained before that takes the current observation, previous state, and previous action to get the current state. And also a decoder that, based on the current state, gives you the reconstructed image or observation. And the loss function just consists of two parts, an image reconstruction loss and a multiple shooting dynamics prediction loss. So graphically, it looks like this. In black here, I'm denoting the sequence of latent states from the encoder. And in blue, it's just the propagated dynamics to generate the state sequence. And the reconstruction loss, basically, it's just that we take the current image, we encode it, we decode it, we take the loss, and the dynamics loss tries to ground the prediction of the dynamics to the encoder sequence. So then we take this loss, we add it to the IDBF loss, and that's our loss for our end-to-end learning procedure. And this is the framework that I showed. And now, given a performance policy, we're ready to solve this problem at every time step and get a control input that keeps us in distribution. So we apply this to a couple of systems. So this is a very simple robot navigation example in which we have an obstacle that is represented by this orange box and a robot that is represented by this blue circle. We only assume that we have these top-down images, so we don't know the location of the robot at any time. And what we have offline is a bunch of demonstrations of the robot navigating in this room without ever hitting the obstacle, and also with the center of the robot never leaving the room limits. So we train our framework using the procedure that I've just described, And then during deployment, if now I give it a reference policy that tells it, hey, go directly to a point that is here and go as straight as possible, so it would completely collide against the obstacle, and then also since the point is outside of the room limits, the center would leave the room. Using the trained model, it actually is able to filter out the actions that would make it collide, so it goes around the obstacle. And given that the objective point is here, it would also try to push the center of the robot outside of the room limits, but the filter doesn't allow it to, so it keeps the center inside of the room limits. And we also apply this to another setting in which now we have first eye views, so egocentric views of a driving simulator. So this is a car, I mean, you don't see the car here because it's first eye view, driving in this corridor. And the reference policy is just trying to drive straight at all times. Doesn't matter if there's a wall or anything, just trying to drive straight. And given that there's an initial angle, if you just apply this reference policy from the beginning, it would collide against the wall. But using, using our filter, before colliding against the wall, it actually rewrites the action to keep it going straight in the corridor. And when a corner approaches, the reference policy would just tell it, hey, keep going straight, which would make it collide against the wall. But our filter actually forces a left turn as the corner approaches, just because it makes it stay in distribution with respect to the demonstrations. So when comparing this to a couple baselines for staying in distribution, one is just using the behavioral cloning model as a filter, so in the sense of only apply high likelihood actions from the behavioral cloning model. And the other one is train an ensemble of dynamics models and just apply actions that give you a low variance of the dynamics. What we see is that we achieve, using our framework, a much lower collision rate in both of the examples. And the only baseline that achieves like a fairly good objective is the behavioral cloning filter being very restrictive, meaning only applying very high likelihood actions, but at the cost of a very high intervention rate, as you can see here. So this is basically a measure of how much the filter is actually rewriting the reference policy. So we don't rewrite it as much and achieve a much lower collision rate. So just to conclude, we present basically a way to try to embed control invariance in a pure end-to-end learning framework by just leveraging ideas from control theory to embed these sort of inductive biases into the learning procedure. And we show that if you take this approach of staying in distribution as a way to stay safe, there is no need here to fail in order to learn how to stay safe. As feature work, we want to move to a probabilistic dynamics model and encoder. Everything right now is deterministic. And the good thing is that this framework is very modular. So we can actually deploy it on much more complex tasks by using pre-trained latents that, the representation learning people have been doing for a while. So thank you, and I'm happy to answer any questions. Here you have a link to the archive paper.
All right, we have time for one question, I think.
Hi, thank you. A very interesting talk. Earlier in the presentation, you mentioned that in order to learn the unsafe set, you were learning it by what experts didn't do. Is that correct?
Sort of, yeah. We train a behavioral model based on the experts, and then, the idea is basically, try to do whatever the experts didn't do. Yeah.
Okay, so so in that case, would that possibly create maybe a very conservative safe set, since it's possible an expert may have a
by safe
action?
set here, I mean the training data distribution. So whatever the experts don't do, I consider it to be unsafe. I'm not exploring outside of the experts' demonstrations. Yeah.
Right. So if an expert didn't do something, it's unsafe. But would it be possible for there still to be safe actions that an expert didn't do?
Yeah, for sure. Yeah, that could be the case. But here we're just trying to stay in distribution. We're not thinking about safety in any other way.
Okay. Sounds good. Thank you.
All right, with that, let's thank all the speakers again, and let's also thank Nick. He's coming up here and he wants to say a few words.
Just a
just a real quick thing. So we're going to have our final coffee break and then poster session across the way. I just wanted to mention that for those of you who have your luggage in near the registration desk here, it'll stay open until about 5:45, so you can leave it here and then come back after the poster session. There'll be somebody watching it the whole time, so you don't have to worry about it. All right, let's thank our speakers again. Thanks, everyone.